Good morning. Good morning. Okay, that's yours. What time do you Usually the traffic at the airport is coming over, but people arriving, or arriving. And that's a nice little airport to arrive. It's not that. One thing I know is like they're doing all There you go. Nice. Sit down. I would forgot that. Awkward to say, you know, talk about it.
Just eating till you pass out. I like your style. Yeah. Yeah.
Well, no, I mean. There's time.
Yeah.
Nima, were you able to incorporate Maria's?
I thank you for .e file to .pdf also.
Amazing. Thank you very much.
Yes.
Yeah. Well, I think. I see you're gonna
All right, everyone, welcome to the last day of summer school. Before we get started this morning with our lecture from Maria Carisi on electromagnetic signatures of supermassive black hole binaries, we're going to have our final student presentation from David Storm, who's a graduate student here. So David, if you'd like to come up and just join the Zoom, and well, maybe it'll be easier to join the Zoom and share screen. Bring your tablet with you. You on the Slack? Yes. And then when you join, just leave the computer audio so we don't get feedback. Okay. Will you go to the arrow there? Leave computer audio. And then you can share your screen. Thanks. Thank you. Sorry. Did you publish?
Yeah, but,
Did you share a screen over there?
yes.
Your first Windows experiment. Sorry. That's okay. Did you send the presentation,
Yes, I did.
to me? There we go. And again, just go to the computer.
So
Yeah, that's it. Thanks.
probably not. Okay. Looks good. Okay. Good morning. My name is David Storm. I'm a fourth year working with Professor Bob Sure, he's in cosmology, and so I'm looking at gravitational waves from Garfinkel-Botch's body cosmic string loops. These are topological defects that I'll describe later, but yeah, I'm using gravitational waves from cosmic string loops rather than binaries or stuff like that. So it's more of a new physics kind of search, but it's still relevant to PTA analysis. There's analysis you can do using PTAs. So yeah, cosmic strings are one-dimensional topological defects. They're formed by spontaneous symmetry breaking in the early universe. Here there are shown three different regions of space here, corresponding to three different regions in the well, showing the phases chose by each region in the Higgs field. So that this Higgs-like field in the early universe spontaneously broke the U1 symmetry. This caused a nucleation, a bubble nucleation in the early universe to spontaneously choose the same phase that was initially chosen in that region of space. And as this spread outwards, this region, this phase chosen by phi, was influencing the space around it, the regions of space around it. As that happens, it kind of moves them towards the full 2 pi around this Higgs-like potential. So this Higgs-like potential is a Mexican hat potential. It got trapped. It has a field initially trapped in the phi equals 0, and that the symmetry breaking is spontaneously choosing a phase at each point in space. And so this nucleates, and as it nucleates, it influences the phase choice from the phi, from the Higgs-like field at all regions of space surrounding it. And eventually this creates something like a vortex, something like a topological defect that does not allow the center to also proceed to spontaneously break its symmetry. So at the center of that, it gets trapped at phi equals 0, a small topological defect. Because it is cylindrically symmetrical, like you can see, it creates a column. This column is created throughout the universe. So this is an infinitely long cosmic string loop that is created in the early universe and might still exist today. Maybe it existed early on. We don't really know yet, but it's theorized. And its primary method of decay is expected to be gravitational waves. So that's how it's relevant, or what we're interested in it. So cosmic strings, they can contain cusps. Cusps are waves that travel along the loop. You can see that a cusp is forming if you see the from t equals 0, t equals 1, t equals 2. is traveling along the loop, and then t equals 7, you can see it's about to have that whip-like cusp, and then at t equals 8 is where the cusp exists. This goes back around the loop until it gets to t equals 0, which is another cusp. So it's an instantaneous speed of light that where along the loop, the wave instantaneously creates a speed of light whip-like cusp, and that cusp radiates a lot of gravitational radiation and particles and other things. But that would be one way that you could detect gravitational waves from cosmic string loops. But another way is from kinks, and kinks would occur. Their production is from intercommutation, where two strings would collide, trade partners here, and kink would proceed down the loop and up the loop at the same time. And those kinks are these corners, or these edges, these discontinuities. And this would, numerical simulations have indicated that the most for string loops, ones that aren't just infinitely long and spanning the universe, or ones that are finite in their length, the average number of kinks per loop would be 4. And so the Garfinkel-Vachaspati loop, which is a 4-segmented piecewise linear loop with 4 kinks, is expected to be the average, or is expected to be the most common type of loop if there are such kinky loops that have that do not have cusps. These loops do not have cusps because there's a 40% chance that from that Coppi-Vachaspati simulation, there's a 40% chance that cusps exist on these loops if they exist. And so taking the 4 segmented Garfinkel-Vachaspati loop that does not have cusps, that's a Garfinkel-Vachaspati loop. Sorry, did I say that twice? A 4-segmented loop that does not have cusps is a Garfinkel-Vachaspati loop. So taking this loop, that's what it looks like as it travels through time, and where the x and the y are just x and y. This is a planar loop. That means that it's lying in a plane, and that's what. So other simulations have found that even when you segment this up into a very large number of segments and linear segments, these do tend to approach a planar loop. And some of these have even found that it approaches a roughly 4-segmented planar loop. So this is a very numerically supported model. And so this is what the world sheet would look like, where the z-axis is time. And the simulation that I'm about to, or the model that I'm about to describe, is going to look at each individual world sheet and observe the gravitational back reaction on these. But more on that in a second. So anyways, the main thing is that this is the equation of motion for the Garfinkel-Vachaspati loops, or most loops. Just the way to make it a Garfinkel-Vachaspati loop is to take A and B, the two functions, and choose 2 segments, make them linear, and add some constants to make sure that they stay centered and connected. And then the 2 main parameters for these loops are the length and the tension. The tension is like the energy density, and the length is just the length. So we were wondering how gravitational back reaction and Garfinkel-Vachaspati loops affects their gravitational waves. So we're looking at their waveform and their total power per mode. For the waveforms, we expect curving, and you'll see why after I show you the gravitationally back reacted loops. And for the background, that one we kind of just expected that they may deviate from expectations, and I'll show you why in a formula as well. So first, before we proceeded, we needed to reproduce the Ohlm-Achter result. Calculated the back reaction at each point. Now all the points are going to see the back reaction, so we don't actually have to do, like, computationally, we don't have to do each and every little segment. This affects the loop form in the way that's shown. It bends it, and it bows it outward as it's in the first part of the period. And then in the second part, it bows it inward. And that's why we expect curving in the waveform. So this is what was previously found by Allen and Odwell in their formalism. They first, they break it down into the H plus and H cross, and just like standard, just like we've been learning throughout this course as well. And then they compute the radiative portion of the metric perturbation. And so just using that same formalism, this is what was found. These are preliminary results and not what's going to be ending up in the paper, but I just figured I'd show some kind of a preview here. And then for the stochastic signals, this is the energy density that you're probably familiar with if you've been reading the new physics directions from the Nanograv 15-year release and stuff like that. So this is a pretty standard energy density formula, but the main thing is that when considering cosmic strings, the common perception has been that n to the negative 4/3 represents cusps, n to the negative 5/3 represents kinks, n to the negative 2 represents kink-kink collisions, and this is partially due to this Garfinkel-Vachaspati result shown right here, which has a n to the negative 2 dependence of power. And this also has some n dependence right here, where it's -1 to the n, also has an independence here, where it's a cosine, and here and here. And so people would look at this and they would say, well, this oscillates from -1 to 1, this oscillates from -1 to 1, so it won't affect the overall result. It'll proceed as n to the negative 2, which is fine for an approximation, but the truth is shown over here when you compute it numerically, which is somewhere between -2 and -5/3. So it's not actually representative of these cosmic string loops, the Garfinkel-Vachaspati loops. So what we found is that this is for a very specific loop where it's perfectly square. There are rectangular Garfinkel-Vachaspati loops, but the main thing is that this has a plus log of n dependence, and so this will change the for larger n's, for larger modes. This will change the power spectrum, and so that's the main consideration here. Not as much of the decay, but the decay is also does cause it to have higher power at larger modes. So that's where we're at. This first step is already complete for my research. The second step is still being pre-published. The third has been pre-published and is now submitted for publication. So yeah, any questions, comments, concerns?
I have two questions. One, you said, I think that the cusps could create particles as well as gravitational waves.
Yes.
Would it be like an actual electromagnetic signature, or is it more particle physics?
So it depends on what theory and what model, but yeah, they can produce cosmic rays, and those can be detected here on Earth. And you'll have to like decide on a model for that to for the answer to your question, I suppose. And I don't know all the models that are there. Sorry.
And my second question was on the energy density. One was 4/3 and one was 5/3. How that's how if it's a mix of both, or multiple, how it's a small difference between the two. How do you know how easily or how easy it'll be to use apart which should be used?
So it sounds like a small difference, but it's these are related to the frequencies, and the frequency what frequencies can detect these cosmic strings is what the exigence is what the point of the models is that where in the frequency spectrum are we looking for these? And if we were to look for these, which ones would we expect to see? The ones with cusps, or the ones with kinks, or the ones with the collisions? And that would depend on their power spectrum. And that's why we're looking at this, is because at what mode determines your frequency range. If you're at a higher frequency range, you're at higher modes, then you're only going to detect may be the ones that are the loudest, the -4/3. Now, if you're looking at lower modes, then you'd be looking at the other ones perhaps. But it just depends on where in the frequency spectrum you're looking. Good question.
Okay, I'm sorry to ask a silly question, but it's something I've always wondered. In cosmic strings, why is the cylindrical potential favored?
So that's due to a couple of reasons. Let's see. To choose, so the cylindrical potential is lambda phi squared, the absolute value of phi squared minus eta squared. And this is because it's one of the simplest ones where if phi takes on a potential eta, it will have the potential go to 0 and be minimized. So that's one of the reasons. And another reason is because it requires that each of these individual spontaneous nucleations can take on their own value of phi without changing the U1 symmetry when it is trapped at phi equals 0. So there are physical reasons for it, which have to be met. There are physical requirements that have to be met. And this is one of the simplest models to make those requirements. That phi, when taking on eta, it minimizes potential. And however, your choice of phase isn't going to, your choice of phase will be independent, but it won't change the U1 symmetry when you get to phi equals 0.
All right, if there are no more questions. This is a very nice teaser of material we hear from Andrea and Daphne pretty soon. Thanks so much, David. So next up, very kindly joining us live from Greece is Maria Carisi, who's going to tell us all about the possible electromagnetic signatures of supermassive black hole binaries. William, were you just waving or were you something to say something? Oh, okay. Okay. Maria, thank you very much for joining us. We've got a group of people here that are eager to hear what you have to say. So whenever you're ready, feel free to share screen.
Hi, everyone. Can you hear me all right?
Yes, sound great.
Okay, let's do that. And you can see the slides and everything?
Yes.
Okay, great. Thanks for the invitation, Steve. Today I'm going to talk about how we can find supermassive black hole binaries using electromagnetic waves, and in particular, time domain data, and also how we can combine this electromagnetic data with pulsar time array data to do multi-messenger science. And of course, you all know this, but supermassive black hole binaries are a natural expectation of galaxy mergers, because every massive galaxy has a supermassive black hole in the center. And following a galaxy merger, we form a galaxy that has two supermassive black holes, which lose energy and angular momentum and progressively move to smaller and smaller separations. When we refer to the binary states, typically we refer to the stage when the two black holes are roughly at a parsec separation, and they are gravitationally bound to each other. So pretty much their orbit is determined by the gravity of the two black holes and nothing around them. So one important thing to keep in mind, especially since this is a talk about electromagnetic signatures, is that when we have galaxy mergers, typically we have a lot of gas that is involved in these mergers. And that gas in the process of the merger is pushed to the central regions of the post-merger galaxy. And it can accrete to the black holes and provide bright electromagnetic emission, which of course for us, this is very important because it will provide the bright signatures that will allow us to find these systems. So over the last 4 decades, we roughly know the stages that the two black holes go through after a galaxy merger. Initially, we have the effects of dynamical friction, which is practically large-scale interactions with the stars and the gas in the newly formed bulbs that push the black holes towards the common gravitational potential. This process is, let's say, efficient up to a few parsec. When we get to the parsec regime, we have interactions with the immediate environment. For example, we have three-body interactions with the stars. If we have a star that crosses the binary orbit, the star can gain some energy and be expelled to large distances. And by that process, in that three-bond interaction, the binary loses some energy. Of course, you can imagine that the star is much smaller than the supermassive binary, and we need many, many such interactions to have a noticeable effect. The other possibility is related to the presence of the gas that I already said we expect to be around the binary. So the gas can also catalyze the binary evolution, removing energy and angular momentum and pushing the binary inwards. And of course, in the end, we have the emission of gravitational waves that can dominate the evolution of the binary in the final stages and lead the two black holes to the merger. And among these three stages, the most uncertain has been the intermediate one. And currently, the consensus, this has been a long-standing problem called the final parsec problem. The consensus in the community is that nature knows how to solve this final parsec problem, and we have quite a few solutions to this problem, but we don't really know which process is the most important and what drives the binary evolution at this stage. And of course, one of the reasons is that in this stage, we don't have observational evidence for supermassive black hole binaries. So we have never confirmed a binary with a separation less than a parsec. So observationally, we very often see the initial stages of galaxy mergers and, of course, the pairing of their black holes. So over the last 2 decades, we have seen a lot of, not a lot, a few dozens of galaxies that have 2 active supermassive black holes, and they're typically separated by kiloparsec distances. So when the 2 black holes are both active and they're at kiloparsec separations, we can resolve them across the electromagnetic spectrum and we have indeed resolved them in X-rays, optical, radio, infrared, and so on. So when we go to smaller separations, taking an image and resolving the 2 black holes becomes much more challenging. And these, when they get to the parsec separation, they can be resolved with a technique called very long baseline interferometry, practically using the entire Earth as a coordinated telescope. And this source here is the record holding binary with a projected separation of 7 parsec. Now, if we go to even smaller separations, and the galaxies that we are trying to resolve are relatively far, there's no telescope that has the required resolution to take an image and see 2 black holes at sub-parsec separation. So we need to infer the presence of the binary from the effect that this binary has in the environment. And I assume Jesse already told you about Doppler sieves in the broad emission lines. I will discuss another potential method, which is to find quasars with periodic variability. So first of all, why quasars? We think at least some of the quasars are activated by galaxy mergers. The process of the galaxy merger brings the gas into the center of the post-merger galaxy, and that can activate the AGN. So looking for 2 black holes in quasars makes sense. And why do we want to find periodic variability? Again, I would argue that this is fairly intuitive. We have an orbiting binary that periodically perturbs its environment. But this is also something that has been confirmed over and over in hydrodynamical simulations. So this is a small video from hydrodynamical simulation where we put 2 black holes in the center of a disk, the black holes act as a propeller and push the gas from the center outwards, so they create a cavity of low-dense material in the center. But again, as the black holes interact with the edge of the cavity, we have streams of material that gets into the cavity and hit the black holes. And we also have gas that gets bound to these black holes individually. So we can have two main mechanisms that produce periodic variability. One is related to these streams that periodically enter the cavity and hit the black holes. So if we look at the accretion rate onto the supermassive black holes, we see that it's periodically modulated. We take the periodogram of this accretion rate and we see peaks at the orbital period. The other possibility is that we have this gas which moves with relativistic velocity, and from relativity alone, we can produce sinusoidal variability. And I'll come back to this signature in a couple of slides. Now, over the last few years, let's say over the last decade, we had a lot of development in this search for quasar periodicity, because for the first time we had the required data. We had a lot of quasar light curves that we could use to search for periodicity. And the reason for this is because we started having these time domain surveys that systematically scan the sky and record how the brightness of millions of sources changes over time. And this is a compilation of the different time domain surveys, from the dark energy survey to PAN-STARRS, PTF, SDSS, which had a time domain component on stripe 82, ZTF, which is the continuation of PTF, but with a much bigger camera, and you can see that it covers a much larger field of view. And then, of course, we will have LSST in just a year or so. So for the first time, we had the data to search for this quasar periodicity, and indeed, by now as a community, we have analyzed most of the time domain data looking for quasar periodicities, and we have identified about 250 candidates. And here there are some snapshots or some examples of these candidates from the different searches. I would like to emphasize that these are candidate systems because finding periodicity in quasars is very hard. You can see that the periods that we are looking for are a few years long, so we don't see repetition of the periodicity. We don't see many cycles. And also we have noisy data with significant gaps and so on. So it's very hard to confirm this periodicity. Apart from these 250 candidates that came out from systematic searches, we also have a few examples that came out serendipitously. I just mentioned a few examples that are interesting. So this is a blazar, for example, that shows periodicity in the late part of the light curve. And then the periodicity doesn't continue, but if we look at historic data, there's also another part that shows periodicity, which is also coherent with the last part. So it seems like the periodicity is turning on and off. And they have a model here to describe it with the jet that is producing, the jet is moving and is producing these periodic oscillations. This spiky source, this is a candidate for self-lensing. So for example, if we have an unequal mass binary, when the small black hole goes, the accretion disk of the small black hole goes behind the accretion, the big black hole, we get a symmetric flare from lensing. And this is one of the AGN that were observed with Kepler. You can see that the quality of the data is very good. And this has a symmetric flare that can be explained with this self-lensing model. This is another interesting source. It was called in the paper, I think, TikTok, because it shows some evidence of oscillatory behavior. It also, in the paper, they claim that the frequency of this oscillation is increasing, which means that the binary, if there's a binary there, it goes towards merger. These follow-up observations didn't confirm this pattern, but this is something interesting. And this is yet another source that was found serendipitously, and it's also micro-lensed. So they have two light curves, and they can correlate the two light curves, and they show this periodic behavior. Now, all of these remain candidates, and a lot of them may possibly prove to be false positives because quasars have stochastic variability. And that stochastic variability can mimic the periodicity. For example, what I'm showing here is one of the prominent candidates, the observations here. And then in the back, there is a simulation of quasar noise. So this is a typical quasar with one single supermassive black hole. And you can see that in the limit of relatively few cycles, it's very hard to distinguish the real periodicity from something which is noise. Of course, this stochastic variability also hinders the detection of real signals. And I think this is something we tend to forget, that even if we had real signals, it's very hard to distinguish them from noise, and we may lose real signals. So we need to observe these binaries for a very long time to confirm that the periodicity remains in the data. But of course, if we have periods of 5 years, like this one, if we want to collect 10 cycles, we need to wait for 50 years. So this is a very long time. Or we need to understand the noise better to be able to distinguish the two models, for example. And you can imagine, typically we describe the quasar variability with what we call a dumb random walk model. But you can imagine that if this dumb random walk fails 1 out of 1,000 times, and binaries are also relatively rare and are found at the rate of 1 over 1,000 times, that can be a problem. So instead of looking long-term, which of course we will be doing for all the candidates we identify, we can also search for additional signatures, like the relativistic Doppler boost that I already mentioned, which is related to this gas that gets bound to individual black holes. So if the binaries are moving, we have a subparsec binary that moves with a period of a few years. The velocities we expect for the individual black holes get to a few percent of the speed of light. So if in addition we have an unequal mass binary, typically the smaller black hole, which is the one that moves closer to the edge of the circumbinary disk, gets brighter. And also it's the one that moves faster. So when the secondary, the smaller black hole, moves towards the observer, we will see something brighter. When it's moving away, we will see something dimmer, even if in the rest frame, the luminosity is constant. And there is a multi-wavelength prediction for this type of signature. For example, if we look at optical and UV data, they should change simultaneously, but the amplitude of the variability can be predicted from the spectral slope. So we have a very concrete prediction that we can test with multi-wavelength data. And I'll just show you an example of a binary that has this type of behavior. So in the top panel, I'm showing you, this is the binary candidate, PG1302. On the top, we have the optical data, which we use to identify this source. And then we fit a Doppler boost model. And then on the bottom, we make a prediction of how the UV data should look like. And you can see that the data fit relatively well this model. The problem is that this signature is not unique. Quasars have wavelength-dependent variability, which can also mimic this periodicity, this type of behavior, not necessarily periodicity. So what happens is the UV light curves are relatively sparse. And when we don't have very good data, by chance, we can also see this behavior. Now, there are also other signatures that one can search for, and this is something we and many other groups have been doing. For example, if we have a binary and it has a jet, the base of the jet will be moving. That will result in a very interesting structure of the jet, like a helical jet or a wiggle jet. I assume that Jesse already talked about spectral signatures. If there is a broad emission line that is moving with the binary, then this can also be imprinted in the broad emission lines, and we will see a coherent Doppler shift in the broad emission lines. We could also see, if we have very precise astrometry, we could see a wiggle of the photocenter, even if we can't distinguish the two sources. And of course, there's the possibility of seeing gravitation waves with PTAs for the most massive binaries, or with LISA for the lower mass binaries. And this is a summary figure from a review we wrote last year, where we summarize all the potential possibilities of the EM signatures, and also we highlight some of the candidates. The bottom line is that there are a few candidates that have multiple lines of evidence, but also none of these signatures that we can examine are unique to the binary. So it's very easy to confuse them with the typical single supermassive black hole quasar. Now, for me, this is a very exciting time because we have the Rubin Observatory that will perform the Legacy Survey of Space and Time, or LSST. And the Rubin Observatory, I think, will be a game changer for the search for quasar periodicity for two main reasons. One is that the quality of the data we expect to be very good. And two, it will observe a huge sample of quasars. So typical, let's say the maximum we have in current time domain surveys, about 100,000. With LSST, we will go to a few million and maybe even to tens of millions of sources. So in that huge sample, we expect to find more rare sources, which are the ones probably that have shorter periods, so they're shorter lived. But because we have such a huge sample, we have the expectation that these sources will be present in the data. So for example, if we find a binary that has a period of 2 months, over the course of the survey, which will be 10 years, we will be able to accumulate many, many cycles. And then we will be confident that this is indeed a periodic source, and therefore a supermassive black hole binary. Now, of course, I told you that finding quasar periodicity is quite challenging, and we get a lot of false positives. So it is possible that with LSST, we will also find a lot of false positives. So with Caitlin Witt, as part of her PhD thesis, we developed a Bayesian pipeline to detect periodic signals from binaries on top of realistic quasar noise. And then we tested our pipeline with data that have properties similar to the current time domain surveys, which is like Catalina, and with properties of something like what we expect for LSST, which is the circles here. So what I'm showing is what we call an ROC curve. So the true positive rate, real signals that should be detected, versus the false positive rate, so noise that is falsely identified as a signal. And then the star is the detection threshold we had with this method. And you see that both with the Catalina data and something like LSST, we find about 60% of the real signal. And the reason for this is the red noise, the stochastic variability. We tried with white noise, and if we had white noise, we would expect, we would find almost all of the signals in LSST. Now, the other important thing with this method is that we go from something that has a false detection rate of about 20% to something that goes almost close to zero. And of course, the reason for this is that the quality of the data of LSST is great. Now, of course, you can imagine this Bayesian method takes a few CPU hours per source. So we cannot just apply it blindly to all the quasars in the LST database. So the data volume we expect from LST will become a problem, and we need to develop more efficient methods to analyze the entire database. Now, another thing that Caitlin found was which binaries we are more likely to detect. So this is the detection rate as a function of the injected period of the signal, the amplitude, and these are the noise parameters. So we see that it's very easy to find the short period binaries, but as we go to longer and longer periods, we start missing a lot of the binaries because we cannot differentiate them from the noise. And similarly, if we have high amplitude signals, so we have strong signals, it's easier to detect them from the noise. Now, in terms of the noise parameters, sigma is again the amplitude of the noise. So when we have high sigma values, again, the signal is buried into the noise and we lose a lot of the signals. And with tau, that seems to have a smaller effect, but it also plays a role here. Now, this is all I had about the pure electromagnetic searches. Let's move on to, let's say, the multi-messenger searches. We are at the point that we have found the first evidence for the background. So we expect that in just a few years, we should be able to detect individual binaries that will stand above the background. And we will detect these binaries a long time before the merger. So for our human timescales, these sources are practically eternal. And of course, they're very exciting because they're promising sources for multi-messenger observations. Because as I already mentioned, we expect that these sources produce bright electromagnetic emission. Now, why do we care about multi-messenger observations? Multi-messenger has become a buzzword in recent years. In fact, Astro 2020, which is the decadal survey, ranked multi-messenger and time domain science as one of the three priorities for the US astronomy. So for the students in the audience that don't know what these decadal surveys are, so every 10 years, the astronomers in the US come together as a community. They write white papers that summarize what are the top priorities in the field, and then there is a panel that reads these white papers and makes some recommendations about what is the top priorities for science. And for this decade, multi-messenger and time domain turns out to be one of the top priorities here. So why? I guess it's because it is the first time we can really do multi-messenger science. We have been detecting gravitational waves for only a few years now. And we want to do multi-messenger science because each different messenger carries different information about the physics of the problem. So for example, gravitational waves probe the orbits and the dynamics of the orbit, whereas electromagnetic observations probe the conditions of the plasma and how it interacts with the binary. So of course, it makes sense to combine both data sets to get the most complete picture of the physics that is involved in these systems. Now, there are two ways to get to multi-messenger detections. The first one is to find gravitational waves and then find the associated electromagnetic counterpart and identify the host galaxy. I assume that Paulina has either already told you about this or she will tell you, so I won't get into this. But I will describe the other possibility, which is to find first electromagnetic candidates like the ones I already described, and then with targeted gravitational wave searches, find evidence for the binary in the gravitational wave data. So why is this important? Is because when we do targeted searches, we gain in sensitivity. So this is a simulation of the same binary. When we do the typical search, which is a completely uninformed all-sky search, and you can see that the detection statistic is below 1, so this is not detectable. But then if we do a targeted search, let's say we know which galaxy to target, so we know the position and distance, or we have some additional information about the total mass of the system or even the period, then we gain some sensitivity. So we go from something that is undetectable with a blind search to something that is significant with a targeted search. Of course, as I mentioned already, with these electromagnetic candidates, we may have a lot of false positives. And I am not entirely sure what happens when you target a false positive, because you practically lower the threshold for detection because you think you know where this binary is. So I would say we need to be careful when we are targeting these electromagnetic candidates, especially since now we are at a regime that we don't have a confident detection yet. Now, of course, it is very exciting that the time domain data or the time domain surveys that I described in the first part of the talk and the pulsar timing arrays can probe the same population of binaries. Actually, in this paper, we looked at the parameter space in terms of total mass of the binary and period of the binary for which we can detect binaries. So the blue shaded region delineates the parameter space of binaries which we can detect with electromagnetic surveys, and the purple is binaries we can detect with gravitational wave data, starting from the nanograph 11-year sensitivity, going to the IPTA 2025, roughly the sensitivity we will have with IPTA DR3, and then projecting the sensitivity 10 years down the line. So you can see that now we are limited to the most massive binaries for multi-messenger observations, but as the sensitivity of PTAs increases, more and more binaries enter this common parameter space. Now, if we want to combine electromagnetic data with gravitational wave data, we need to connect the parameters with the orbital parameters of the binary. And we realized that if we have the case of relativistic Doppler boost that I was describing before, we can connect many of the EM parameters to the gravitational wave parameters. So for example, the period, the observed period is the orbital period of the binary. So the frequency of the gravitational wave will be twice the orbital frequency of the binary. The amplitude here depends on parameters like the mass ratio or the total mass of the binary, the inclination, which also define the strength of the gravitational waves. And maybe we can also combine information about the phase. When we are thinking about periodic accretion, we have two regimes. If we are at the low mass ratio regime, then again, the orbital period of the binary is the observed period, so we can link that to the gravitational wave frequency. But if we have high mass ratio binaries, in that case, maybe the observed period won't be the orbital period of the binary, but it will be the orbital period of a hotspot that is formed at the edge of the circumbinary cavity. And then it will be a few times the orbital period of the binary, so that makes the connection with the gravitational wave frequency a bit more tentative. Now, why we want to do that? Of course, one of the reasons is that if we look at the gravitational wave signal and the, let's say, corresponding electromagnetic signal in the case of Doppler boost, and we get the parameter constraints by analyzing each signal individually, we get very broad constraints from each one. But if we put them together, we can get better constraints. So this is something that I'm currently working on. We are simulating a population of binaries, and then we are looking at the parameter constraints. So these are different parameters like the gravitational wave frequency, the binary mass, the mass ratio, and so on. And we analyze the signals. We analyze first only the electromagnetic signal, then only the gravitational wave signal, and then we do a joint analysis like a multi-messenger pipeline. And then we look at the, let's say, percent error of the parameter constraints, and you can see that typically the multi-messenger constraints are more peaked around 0. So we get better constraints when we do the multi-messenger analysis compared to when we analyze the data individually. So this is something we are currently working on, and hopefully you'll hear more about this. Another interesting thing we kind of stumbled upon when we were doing this type of search is that when you do multi-messenger searches, by default, you have to do a targeted search. As I said, we have these electromagnetic candidates that we target. We know where exactly they are, which galaxy, which distance. So when we do targeted, when we do a typical gravitational wave search, we have the Earth term, which is common to all. It is from the deviations of when the gravitational wave passes the Earth, and we have individual pulsar terms which are different for each pulsar. And this is from when the gravitational wave passed each pulsar. Now, in targeted searches, we can omit the pulsar terms, which actually makes the searches much faster. And here, again, I'm showing the percent error for the different gravitational wave parameters, like the frequency, the total mass, the mass ratio, for a population of binaries. And you see we get very similar distributions, both with the full signal, which includes the pulsar terms, but also if we omit the pulsar terms and we do an Earth term analysis only. But what is important is that when we turn off the pulsar terms, we get a much faster analysis. So you can see here when we look at the autocorrelation length of the MCMC chains as an estimate of how fast we can run the searches, the Earth term is almost 100 times faster than the full signal analysis. So if we're doing targeted searches, we can omit the pulsar terms without losing much information about the parameter constraints, but we gain a lot in speed. And this is, I just described the combination of periodic variability with continuous waves, but this is just one of the many possibilities we can do to do multi-messenger science. I will just refer you to this white paper we wrote a few years ago to see what are the possibilities and the open questions in the field. And with that, I'll just go through a quick summary of what I discussed before we can go to questions. So binaries should produce bright electromagnetic emission that can be identified as quasars with periodic variability. Already we have about 250 candidates from the initial searches in time domain surveys, but these candidates are very hard to confirm because we have this stochastic noise and we don't have many cycles of periodicity. Of course, we have LSST that will start operating next year, and we will have, hopefully, a lot more binary candidates. Now, these binaries can also be detected with gravitational waves. Hopefully, very soon, we will see sources above the gravitational wave background. And then we can combine with electromagnetic data and do multi-messenger science. And I showed you that PTAs and time domain surveys can work very nicely together because they probe binaries with similar masses and periods. And as the sensitivity of PTAs becomes better and better, we have more and more binaries that can be detected both with gravitational waves and with electromagnetic data. Now, if we combine electromagnetic and gravitational wave data, of course, we can get better constraints on the parameters of the binaries. And finally, if we are doing multi-messenger searches, they're by default targeted. And as I showed you, we can meet the pulsar terms in the analysis and do a much faster Earth term analysis. So this is all I had for the first part. So we can stop here and see if there are any questions.
Thanks, Maria. So if people have any questions at this point, then that's to go up to the hour. Anything from that? Oh, Levi had a question.
Hi, Maria. Great talk. I was curious, on the bit about the Earth term searches performing similar constraints, how that had to have that has to break down at some point when the signal becomes loud enough, right? And this pulsar term becomes too important. What range of like signal to noise ratios did you explore?
I think you're right about that. So I think what we ended up including in the paper was something between SNR 5 and 15. So we didn't include extremely loud signals, but you're right. Like for some parameters, we do see some differences, but I would say for the two main parameters, which is for me, the frequency of the gravitational wave and the total mass, we pretty much see almost identical distributions, at least for this range of SNR.
And my other question was on some of that work you were showing that's preliminary about multi-messenger searches. You were talking about better constraints than using EM priors. This is like putting your priors from electromagnetic information into your gravitational wave search.
Yeah, so this is something I didn't even mention. Thanks for asking, Levi. So yes, so one of the things we tried was to do the EM analysis and then use the posteriors of the EM of the light curve as priors for the gravitational wave analysis. And then we did the joint likelihood analysis. And we get better constraints when we do the joint likelihood. And this is something we need to understand better, but we think there are some degeneracies in the data that are not captured by just providing the prior. So when you do the joint likelihood analysis, you can somewhat break these degeneracies.
Okay, thank you.
Hi Maria, thanks. I have three questions. So my first question is that regarding targeted searches, you said that if we just keep the Earth term and remove the pulsar term, the signal should not change much. But sometimes we see that when the pulsar term is included, the behavior of some pulsars really affect how the signal looks like. So is it recommended that sometimes when we see this behavior with the pulsar term, we should just remove the pulsar terms, see how the Earth term looks like, and then accordingly decide which pulsars to remove?
So I don't have a good answer to that, but I would say, generally speaking, if we want to target computational demands have been a limitation in these targeted searches, as you probably know. So if we want, and typically what we do is we make some arbitrary cuts or some cuts, and then we'll say we will just target these few sources because we cannot do all of them. But I would suggest that first, we can do the Earth term searches, which are very cheap and easy to set up. And then if we have something interesting, then we can follow up with the more detailed pulsar term searches. So you can think of it as a way to rank which candidates, or like as an initial first filter for which candidates to do the more expensive pulsar term searches.
Okay, thank you. My second question was, could you explain the periodic accretion versus Doppler boosting for quasars? I didn't fully understand that.
Right. So there are two, as I said, there are two potential ways to produce this periodicity. So for example, let's see, we have this disk where you get this cavity, you get this gap in the center. And we have streams of material that enter this cavity and will hit the black hole. So this is what the accretion rate looks like, right? So we draw a circle around the cavity and we see how much of the gas enters and hits each black hole. So this is the accretion rate on the secondary. This is the green, and the primary is the blue. So you see that the accretion rate, so the feeding rate of the black holes, is periodic. So we expect that this will also be translated into periodic variability. So if you look at a light curve, this accretion rate should be translated to some sort of periodicity. Is that part clear?
Yeah.
So the other possibility, you can forget that you have these streams that enter the cavity. The important thing to remember is that you have gas that gets bound to the individual black holes and moves with the black holes. And we have speeds of a few percent of the speed of light. So let's focus on one of the black holes now. Typically, the secondary is brighter and will dominate the periodicity. So this has to do with conservation of energy and photons. So practically, when this one is moving towards the observer, it appears brighter. When it's moving away, it appears dimmer. Even it's like I take a light bulb and I'm moving it with relativistic velocity back and forth. So I get this almost sinusoidal periodicity. This is just special relativity.
Okay. Thank you. And my last question was, you spoke about binaries which are being observed, which will be observed with the LSST. So there are a lot of them which we don't sort of do targeted searches with PTAs. Is it simply because we are not sensitive to them?
So can you repeat? Yes. So, can you repeat the last part of the question?
Yeah, is it that we are not going to observe a lot of the binaries? Like, is it that we are not going to do targeted searches on a lot of LSST observed binaries with PTAs because we are not sensitive to them?
So the thing is, with LSST, we will find a lot more binaries just because we have a lot more quasars to target. So if we want to do a detailed full signal analysis, I think it will be hard to do it for all the LSST binaries. But as you alluded to it, some of the LSST candidates that we will find will be high redshift. So they're not we are not sensitive to these sources. So it doesn't make much sense to do a targeted search for a binary that is at redshift 2, let's say. But if we have a binary at redshift 0.5, I think maybe that's worth doing a targeted search.
Thanks a lot.
Thank you.
Do we have other questions? Yeah, go ahead.
How does the owl work anyway? Okay, cool. Hi. So I had a question about the different kinds of so you mentioned earlier that quasars have some stochastic noise associated with them, like naturally. In a binary system, the driving fundamentals of this are like so different than a singular source. Should we be worried that this sort of quasar noise is some way different than like a regular quasar that has some stochastic noise?
Yes, ideally, yes, that's the idea that when you have two black holes, you should expect to have like resistant periodic signal. either that's sinusoidal or repeated, let's say, periodic pulses or the self-lensing scenario. But the complication is typically you have a long period. These binaries have periods of a few years. And then you end up observing maybe a couple of cycles. And then you have this population of AGN that we have studied, the typical AGN behavior. We know that they have stochastic variability. And the trick is, even though we expect to have different signals, how can you tell them apart when one signal looks like this and the other signal looks like the pink line, and you have the limited data, which also have gaps and everything. And practically when you fit both models, they fit perfectly. So how can you tell them apart? That's the challenge.
Okay. So if we were to understand this, any distinction between these two systems, it'd be easier to find them, even if we don't have a actual period to fully measure.
Yeah. Actually, that's a very good point. Maybe the periodicity is not the correct signature to be looking. We should be looking at another signature. I assume that Jesse talked about this spectral line, so I didn't go much into it. Maybe that's one of the signatures that we should be looking at. Maybe the spectra in X-rays will look different. But so far, and that was the point of this review, we looked at all of the proposed signatures in the literature. And one of the things that comes out is that, yes, there are a lot of signatures and a lot of the things that we say, okay, this would be how a binary looks like. But then if you look at the real data, even a simple quasar, a typical quasar, does something similar, or at least in the limit of low quality data. You cannot distinguish the two. So I was talking about this Doppler boost signature, and you can see it's very hard to get a UV light curve because you can get UV data only from space, so you get a very sparse light curve. If you had a perfectly sampled UV light curve, maybe it would be much easier to say this is the binary and this is the typical quasar behavior.
Cool, thank you.
Yeah.
I have a question. In these searchers, it seems, what has been the method more successful? It seems like you're only doing like Lumps-Cargill, or do you do any other periodicity that doesn't assume sinusoidal? And my second question was about the color. Can you use somehow all of the colors together? Because I guess LSST will have a bunch of colors, or do you do the periodicity searches in each band, or is there a way that you merge them?
So these searches have only searched for sinusoidal periodicity. So we do actually expect that binaries may produce more complex sinusoidal profiles, or non-sinusoidal, more complex periodic non-sinusoidal profiles, but it's kind of harder because we don't have very good expectations from the theoretical side, so you don't have the templates. That's one of the reasons. But I would say, like, if we consider these searches as the first generation of binary searches, then the second generation, which will be more mature, they should look for non-sinusoidal signals. That's one for sure. I can tell you the details for how I did the search, which was definitely based on the Lumps-Cargill periodogram and then modeling the stochastic noise. Different papers used somewhat different methods. For example, this one, I think, used a Lumps-Cargill, but then in the end, they did a Bayesian model selection. But overall, yes, we looked for sinusoidal signals. All of them somewhat modeled the stochastic noise as a damn random walk. And then the other question was whether we use single band data. So far, this has roughly been the case. For LSST, as you said, it will be important to do multi-band periodicity searches, and I'm not sure that we know how to do it.
Thank you.
Hi, I just had a question about the like part of the electromagnetic spectrum you're looking at for these searches. Like what exactly part of the spectrum are you looking in, and like what's the motivation for that compared to other parts of the spectrum?
Yeah, so the periodicity searches, they have been mostly with optical data. And the reason is the availability of data. So we have optical time domain surveys that have observed thousands or 100,000 quasars, and they provide light curves like that. There has been a search with X-ray data, X-ray time domain data, but that was limited to about 1,000 quasars. And you really need the big samples because you are searching for something that is relatively rare. Now, with eROSITA and other telescopes coming online, maybe we will be able to do systematic searches in other parts of the electromagnetic spectrum. That being said, for example, this quasar is in radio. So people have started doing it across the electromagnetic spectrum. There are a few candidates that were found. We found as a community periodicity in gamma rays from light curves from the Fermi telescope. So people are trying to do these periodicity searches across the electromagnetic spectrum. But I would say in the optical community, we're a bit ahead because of the availability of data.
Okay, that makes sense. Thank you.
Thanks.
I think that's all questions for now. Maria, did you have another part to get onto?
Yeah, how much time do I have?
As much time as you like, but probably like maybe 30 to 40 minutes.
Okay, so I put together a notebook that pretty much goes through some of the concepts of what is a light curve and how we can use Lomskargel periodograms. And I think Nima has already uploaded that on GitHub. So you guys can, in your own time, just go through the notebook. So I'll just share my screen again and show you the notebook. So I just wanted to go through this notebook. It has very basic things of what is a light curve and how we can analyze a light curve to search for periodicity, and a little bit about this quasar noise that I described. So when we do photometric searches for binaries, the thing that we are analyzing is a light curve. And for the gravitational wave astronomers in the audience, I thought I need to introduce what a light curve is. So again, these light curves are the product of time domain surveys which systematically scan the sky. So the data set we have is relatively simple for each source. So we have the time of observation. Typically, this is expressed in modified Julian days. So it's something like 58,823.5 days. I think this is for historical reasons, and I cannot defend this choice, but it doesn't matter. But you will see that you will get some weird units here. Then we typically have a brightness, or if we are looking at optical or UV light curves, we typically express that in magnitudes. So in X-rays or radio waves, we typically have fluxes. But again, for historical reasons, in optical or UV surveys, we get the magnitudes, which is the logarithm of the flux. Then we get, for each observations, we get an observation error, and sometimes we can get additional information, which pretty much reflects the quality of the data. For example, did we have good weather? Did we have good seeing? Did something weird happen to the telescope? So you usually get these flags, some quality measures of your observation that you can use to filter out some data. I already mentioned that we have several time domain surveys. A lot of them are still ongoing and they have public data. So I included some links to the databases. So pretty much you can click any of these and go and search for a light curve of your favorite source. Typically, you need to provide the coordinates of the source and an area, like how much around this source they should search for. Because we are talking about optical data, if you include something like 3 arc seconds, you will get probably the correct source. Of course, this is if you want to do a search one by one. In some cases, you can really search for a lot of sources. So a lot of them have SQL capabilities. So you can either upload the text file or write some code to extract a lot of light curves together. So I thought as an example, we will use this PG1302 candidate, which is one of the first that came out from the time domain surveys. And actually, we can do it in real time. So in the data that I have uploaded in GitHub, you will have these 2 light curves. One was the one that was published in this Nature paper by Graham et al. And the other one contains some more recent data from the Assassin survey. So we can plot these two, and this here I'm plotting the initial light curve that was published in Graham in 2015 with red. And then with blue, I plot the newer data that were collected by this Assassin survey. And you can see that one of the challenges when we have light curves is that we need to calibrate the 2 light curves. So what we typically do is we take data that are simultaneous in both light curves, if we are lucky and we have data that are simultaneous. And then we are trying to find what is the correct offset. Here I played a bit with it, and I found that if I impose an offset of 0.3 based on the common part of the 2 light curves, I can bring the light curves together. Now, this is a bit technical, but it ends up being important because if you mess up the calibration, you can either introduce fake noise, or you can reject the periodicity because you didn't calibrate the data. Like if I showed you this light curve and I said this is the reality, you wouldn't say it's periodic. If I showed you this light curve, then the pattern looks more obvious. So calibrating light curves from different surveys, it's quite challenging and technical, but it's something that it turns out to be very important, and I assume it will also be important when we get to LSST because we also have historical data from these time domain surveys that we will want to use, especially since I argued that having long baselines is very important for finding these long-term periodicities. Then the next part is that we want to find periodicity, and one of the tools is this Lomskargol periodogram. So practically, the periodogram is the spectral density of the time series. So for example, if we had nice, evenly sampled data, which is what other experiments like LIGO or the Kepler telescope have, or Fermi, then pretty much we can do a Fourier transform and we can find the spectral density. But typically, with time domain surveys that are the ground-based time domain surveys, we don't have this perfect sampling. Why is that? Of course, the source can go behind the sun. So for a few months every year, we cannot see the source. The source may be at the edge of what the telescope can see for, again, some time over the year. And then we also have things like weather. Maybe one day we have clouds and we cannot observe. So we get gaps and they're not, you cannot avoid them in optical data. There are other things that can happen. For example, the telescope may have a failure or some filter may fail. So we do get gaps and we need to deal with them. So the Lomskargel periodogram comes from these two papers from back in the 80s. And the idea there is that you pretty much do a chi-square fit. So you take sinusoids of different frequencies and you fit the data. And by doing some smart math, you get the equivalent of a Fourier transform in the unevenly sampled data. So what I set out to do here, I'm creating periodic light curves in evenly sampled data. So you see, I choose about a light curve of 1,000 days and I sample it every 5 days. This is something you guys can play. And then I generate a sinusoidal curve, which has three parameters. One is the amplitude, one is the period, and one is the phase, which I set it here. And then I can add also some photometric error, which is the measurement error. And then I can make a very nice sinusoidal curve. Then I use this Lomskargel periodogram from AstroML. There are other packages you can also use. And then I need to provide some test frequencies for the periodogram to be computed. As I said, we do a chi-square fit for each given frequency. So we define which frequencies we can probe. The minimum frequency we can probe is determined by the baseline of the light curve. So let's say the maximum we can observe is a cycle of the period. And then the maximum, the highest frequency, the maximum frequency, is determined by how fast we are taking data. So here I set my frequencies that we will test. So I get a linear space between the minimum and the maximum. You can change again the number. And you can see that this is the light curve and this is the periodogram. And I get a huge peak at the input period. Now, if you want to play with this, I have different ideas for you to try. You can change the amplitude of the sinusoid or change the photometric noise. At some point, you can have like a very small amplitude and the photometric errors can be bigger. And then you will see that this peak becomes much smaller. Then, of course, this was the idealized case of having evenly sampled data. As I said, reality is usually more complicated and we don't have evenly sampled data. So what I will do now is I will create periodic curves, sinusoidal curves, but instead of having like this evenly spaced grid of observations, I will use the actual observed data. So I will make this, I'm injecting a sinusoid here. You cannot see it by eye, like here, because my data are more sparse. And then again, I'll take the periodogram. And you will see that even in the case of sparse and evenly sampled data, I do get a huge peak at the correct period. But unlike before, that this was the only peak and nothing else, now I start getting these fake peaks, which are called aliasing, and these have to do with the sampling of the data. So I'm just going to give you an example of how this aliasing works. Pretty much, we don't have, let's say, high sampling rate. We don't sample the light curve high enough, and that can introduce fake peaks. So, for example, I try here a light curve. All my observations are at 0, but then I set my frequency, my test frequency for the sinusoid higher than the observed rate. And then you can see that very easily I can fit sinusoids that go through this. So my periodogram, because it's a chi-square fit, it will give a perfect fit and therefore a peak for this sinusoid, even though I don't have any signal. So this is something we need to take into account when we are looking for periodicity in sparse, unevenly sampled data. Now, once we have a peak, let's say, in the periodogram, the next thing we need to ask is, what is the probability that this peak arises by chance? Or what is the probability that the noise, whatever noise we assume, can produce this peak? And there are different methods that people try. One is bootstrapping, so removing some of the observations and trying the periodogram in the rest of them, or scrambling, which practically changes the data points or the sequence of the data points. Now, when we have stochastic variability, that becomes a bit more challenging, and you need to explicitly model the noise. So what I am showing here is the power spectral density of this dumb random walk model, which is a really good description of quasar noise, maybe not the perfect. And if I plot this power spectral density, you see that at low frequencies, we have a very flat power spectrum, which is what we expect for white noise, so completely uncorrelated noise. But if we go to high frequencies, we have a dependence of 1 over f squared, which is what we typically call red noise. So typically, when we want to search for periodicity in quasars, we need to model this power spectrum. So I'm giving you here some code to generate dumb random walk time series. You need to provide how many data points you want, what is the time intervals that you want to sample your light curves, and also the dumb random walk parameters. And we can play with that. So here I'm giving the parameters, I'm making a light curve, and then I can rerun the code. I'm having a different realization of the noise. And again, if I change the parameters, you will see that the noise also will change. You can also play with that. And this is one of the complications, that you need to model this underlying noise, which if you play enough, you can convince yourself that you can get periodic looking signals. So this is mostly what I had. I have a mention about trial factors. Typically, when you look at a big sample of quasars, then you increase your chance of finding something randomly. This is something you need to include in your statistics and so on. But this is mostly what I wanted to cover. And I can either leave time for you to play with this or have some time for questions.
Thank you, Maria. So we have time for questions or just free hacking on that notebook. We've got another, say, 15 to 20 minutes in the session, and then we can have a break before we get on to the next lecture on cosmological gravitational waves. Do we have any questions or things that are coming up while you're accessing Maria's notebook? All right, so we can just have independent work time on that notebook. And Maria, if you're available to stay around for about 10 minutes, just in case anything comes up, that would be great. Otherwise, people can post questions in the Slack for you.
Sounds good. I'll stick around for a bit. I'll turn off my camera, but I'll be here.
Sounds great. Thanks, Maria.
Thank you.
Hello, Maria.
Hello.
I have another question about variability, if that's okay. And it's about like QPOs. I know a lot of like quasi-periodic oscillation. I know a lot of people are looking for them. What is the physical mechanism of this? And could that be could that help somehow to find these binaries? And do we expect QPOs in these binaries?
Yeah, so QPOs can arise in accretion disks. So the idea is that you form, maybe one explanation is you form a hotspot in the accretion disk, and that moves around, right? And that can also give rise to something that looks oscillatory in the light curve. Now, for us, that's a complication because you may see a QPO and you may think, oh, this is periodicity, so therefore it's a binary. So for us, it's like a confusion source. The good news is that you can separate the two. The QPO won't be persistent. So it will stay there for a few cycles, but then it will dissipate because we don't expect these things, these formations in the disk to last forever. Whereas a binary will stay there forever and keep doing the same periodicity. So if it dissipates, it's not a persistent periodicity. So maybe it's a QPO. And understanding how to model the QPOs better or how often they happen, I think it's a really good thing for us to do because it will allow us to distinguish the two sources.
But when you say, so what are the timescales of the QPOs that people have searched in AGNs? And are they the same sort of timescales of the orbital periods, or what are the, because you said several cycles.
It depends on the data. When they have like X-ray data, they search for much shorter time scales. But in the optical, because the disk is more extended, you can go to a few, 2 years time scales, right? And that's why you can get confused with the binaries. I think in the X-rays where you search for QPOs of a few hours, I think it's very unlikely that you have a binary with a period of a few hours.
That's cool. Very nice. Thank you again. Great talk. Really enjoyed it.
So folks that are running these hybrid simulations now have a batch where they're just interpolating
Are we getting picked up? Hi. I just want to ask, what do you think the source of like the regular not binary noise, like that sort of that stochastic variability, where do you think that's coming from physically?
It's for sure from the accretion disk. This dumb random walk model is an empirical description. So we get the light curves, we get many light curves, and we see that it can describe. Now, which model in the few papers that I linked in the notebook, there are some explanations, like you have, for example, things that are happening in the accretion disk, like explosions of stars or something like that. And they have some discussions on which models fit and which doesn't, especially the Kelly 2009 paper. But in reality, I would say we don't really know. It's some accretion process, but we don't know exactly what's happening in the accretion disk. And the other thing that I would say is like when we have accretion processes, even in smaller black holes, so X-ray binaries and things like that, we typically get some sort of stochastic variability. So it's not only quasars, it's also other accretion processes that can produce red or pink noise depending on the slope of the power spectrum.
I mean, aren't the smaller black holes usually typically paired up in binaries anyway?
I don't think that's always the case, right?
No? Okay. Okay, thank you.
Yeah. And then yeah, right. Don't you, yeah, oh, yeah, dude. We're just gonna take a lot of sheets and it's like the documents. You just probably, they're just fine with this problem. I would like you. No, you're not. You're not.
Only specific question. But some of the variables were the change seems to just get stuck. No, so this is for
Well. Right. Yeah. I get it, some very change that is. But it seems to just not primary.
It's like, it's so hard.
So I look at the.
Actually, all of it is updated term. Yeah.
Hi again. Is it me? Oh, there you go.
Right.
Sorry, I keep coming up here. But you made me think. You mentioned smaller mass binaries or smaller mass black hole systems, right? Are those directly scalable? Like observing smaller mass accretion, is that the same as observing these larger mass systems? Because as far as I understand, I just took DR, so like I'm very rusty or very unfamiliar with this, but as you increase the mass, the Schwarzschild radius doesn't increase linearly with that, increases like with the square instead of with the cube. So like the innermost stable circular orbit shouldn't be exactly the same, right? Or am I wrong?
So I think it's a good question that I don't really have the answer whether they are scalable. In some cases, even planets around this binary star have a similar behavior in the disk that they form. So sometimes it doesn't matter if it's a black hole or a binary star with a planet, you can get the same physics. So I would assume some of the physics must be scalable, but I don't know. And I think typically when they simulate the things, they do it in massless units, so you can scale it as much as you want. I think some of the physics wouldn't hold, but I don't know the details of that.
But just accretion physics in general.
Yeah, I mean, I think a lot of the simulations can be applied either to stellar mass binaries or supermassive binaries. But I guess the real test will be once we have observations of supermassive binaries, just try and compare with the phenomenology of for example, X-ray binaries,
Uh-huh,
which are step mass binaries, right?
yeah, they're a lot easier to see. Okay, this is something I'll look into, thank you.
Thanks.
Operation, it's. When we take it out of Jupiter also.
All right, well, given that we're just past the hour now, I think let's thank Maria so much for her time.
Thank you. Have the rest of your Fridays.
Thanks, Maria. So we'll take a bit of an extended break now until 11:30. That'll give you more time to play around with that code and then have some coffee and snacks. After that, we'll have a lecture from Andrea Mitrodati, who's right here, on cosmological sources of gravitational waves. And you've had a sneak peek of that material in David Storm's presentation this morning, so it'll be more about relic gravitational waves from inflation, cosmic strings, etc. So thanks again, Maria. Okay, everyone. If you've had quite enough of binaries and you want to know more about cosmological processes in the very early universe that could generate gravitational wave signals that would lie in the PTA band and give us another compelling, really, really cool signal to look for, Andrea Mitrodati is going to tell us all about that. Andrea is co-chair of the Nanograv New Physics Working Group and was one of the lead authors of that monumental paper that came from the New Physics Working Group last year, looking at all of different cosmological signals. And so is an expert in this area. We're very grateful for your time, Andrea. Thank you very much. And whenever you're ready, please go ahead.
Yes, thanks a lot, Steve. Let me share my screen. Okay. Can you hear me all right?
Yes.
Yes. Okay, great. So, as Steve was saying, I'm sure you heard a lot about the gravitational wave background during this week and about the possibility that this background is produced by this cosmic population of supermassive black hole binaries. During this hour, we're going to discuss an alternative to that interpretation of the background, meaning gravitational waves which were produced in the early universe. And during this talk, for early universe, I mean anything that was prior to the emission of the CMB radiation. So this possibility, the possibility that this background was produced early on in cosmic history, has generated a lot of attention and enthusiasm in the high energy physics community. So I'll start discussing why the high energy community is so excited about the possibility that we are seeing a primordial signal of gravitational waves. Then instead of giving you kind of an endless list of all the possible sources of gravitational waves in the early universe, I will try to argue on more general grounds what are the properties that you should expect from these cosmological gravitational wave backgrounds. And then I'll give you two examples of processes in the early universe that can generate gravitational waves. And then we will finish on a more practical note, meaning how we can search for this gravitational wave signal from the early universe in PTA data using PTArcade, which is this wrapper of Kepfield and Enterprise that we wrote within the Nanograv New Physics Working Group. And the idea of this wrapper is to make very easy for people to search for these new physics signals in PTA. Okay, so let's start from the first point. Why all the excitement in the high energy community about the PTA results? So this is a slide that I think I showed at the Nanograv Spring meeting in 2023, last year. So each dot in this slide, it's a paper, it's a work in the field. The size of the dots depends on the number of citations that this paper received. And here, this red dot is the Nanograv 12.5 year dataset, where for the first time, it was shown that there was this hint for a gravitational wave background in our data. And all these white dots connected to it are the papers that cited it. So not surprisingly, we got a lot of citations from the astro community, but also there were a lot of citations coming from the high energy community, which are all these green and blue dots. And the situation has not changed with the 15-year data release, which is what is shown in this slide. Again, a lot of citations and a lot of them coming from the high energy community. And indeed, if you check the four most cited papers in the field last year were the four evidence papers by Nanograv, EPTA, Parks, and the Chinese PTA. And the fifth most cited was the Nanograv New Physics paper. So clearly there is a lot of excitement in the high energy community, and let's try to understand why. And I think if we want to understand why, it's good to kind of highlight and summarize very quickly what are the big open problems in high energy physics, particle physics, cosmology. And I will spare you the theoretical problems related to the internal consistency of our theories. I will just focus on the experimental ones. So what are the experimental observations that our models cannot explain? And one of these observations is the asymmetry between matter and antimatter. Like we look at the universe, we see all these stars, all these structures, but all this stuff is made of matter. So there is no equivalent made of antimatter. So we would like to explain what broke the symmetry between matter and antimatter in the early universe. And right now we don't really have an explanation. We don't really know what broke this symmetry early on in the universe history. Another big problem is dark matter. So we know it's there, but we don't really know what it is. There is no particle within the standard model of particle physics that has the properties that we know dark matter needs to have. Then we know that there is this form of dark energy driving the expansion of the universe. And there again, we don't really know what it is. And then we know that very early on in universe history, there was this stage of exponential expansion, and we don't really know what was driving it. We don't have a particle model that can describe this early stage of exponential expansion of our universe. So there are all these big problems, and we would like to solve them, right? We would like to extend our models to try to explain some of these processes. And one way in which we think we could gain some insight in how to solve these problems is to understand what was going on in the early universe. So, for example, we know that inflation had to take place in the early universe, but also we know that dark matter and this asymmetry between matter and antimatter had to be produced in these early stages of the cosmic history. So it seems quite easy. We should just look very far in these early stages of the cosmic history, and hopefully we will gain some insight on how to solve all these big problems, right? And we cannot know how to look into the past of our cosmic history, since light propagates at finite speed. We know that looking at very far objects, it's equivalent to looking into the past, right? So just look at very high redshifts, and you will see what was going on in these early stages of cosmic history. So it seems easy enough, but there is a problem. So this game of looking far as a way to look into the past kind of breaks down when you want to probe the universe prior to recombination. And the problem is that prior to recombination, the universe was filled with a plasma of charged particles. Electrons and protons were not yet recombined into neutral hydrogen atoms, so you had this plasma, very dense plasma of charged particles. So if you imagine that you had some source in the early universe, which we would like to probe, and this source produce a lot of photons, these photons will just bounce around these charged particles with a mean free path, which is around the order of micrometers. So these photons will just continuously bounce around with these charged particles in the plasma. They will thermalize, and they will lose any information that was imprinted into them by the source. So even if we receive these photons from the CMB, all the information that was imprinted into them from these early universe sources will be lost. However, if this source also produces some signal in gravitational waves, these gravitational waves will not care about plasma. The interaction between gravitational waves and matter is so small, which, yes, makes them very hard to interact, to detect. But in this case, this plays in our advantage, because these weak interactions are so weak that these gravitational waves could propagate freely through this very dense plasma of charged particles. So we could detect them today. And any information that was imprinted into these primordial gravitational waves will remain, and we could use it, if we detect them, to learn something about these primordial sources. So this is why people are so excited that we are seeing a gravitational wave background, and that this background could have been produced in the early units. Because if this is the case, this detection of the background will give us the first glimpse into the dynamic of the universe at times which we are not able to probe just using electromagnetic radiation. So this is the big picture of why people in the high energy community are so excited about PTA's result. So now I'll try to go into a bit more details about the properties of these gravitational wave signals that we should expect to receive from the early universe. Before doing that, let me just set some notations that I will use in the rest of the talk. So I think you've already seen something like this. So this is essentially how we describe gravitational wave background. So on the left, you have this Hij, which is a tensor that describes metric perturbation associated with the background at some time p and position x. So the way in which describe this gravitational wave background is to decompose them in plane waves. These are the plane waves. Then you have the usual polarization tensor of the gravitational wave radiation. And then you have these, let's say, Fourier components that fully characterize the background. Right? If you can compute these functions, you have fully characterized your metric perturbation. Now, in general, we cannot predict the values of these coefficients. So the way in which we treat them is to treat them like random variables. We usually assume that these are Gaussian random variables with zero mean. So all you have to specify to characterize the background is the 2-point function. So the expectation value of the product of these coefficients. And for an unpolarized and stationary background, this 2-point function is uniquely characterized by the power spectrum of the gravitational wave background, and which is telling you how the power of the background is distributed across frequencies. And then you have the power map of the background, which is telling you how the power that you're receiving from the universe is distributed in the sky. Okay, so if you assume that the background is isotropic, this power map is just a constant. You can forget about it. And the only thing that you need to specify to fully characterize the background is the power spectrum. Okay. Now, I think you already saw this during this week. The only subtlety is that typically in the high energy community, instead of using this parametrization, we use an equivalent one. So what I just discussed is this way of parameterizing the background. You specify the 2-point function of these Fourier components. Typically, instead, what we do in the energy physics community is to characterize the background in terms of its contribution to the energy of the universe per logarithmic frequency interval, which is this omega gravitational wave function. So this function, it's in a one-to-one relation with this gravitational wave power spectrum. So specifying the power spectrum of this omega function is exactly the same, right? They are equivalent. And some people use even another way of describing the background, which is giving its characteristic strain. All these three ways of describing the backgrounds are equivalent. All these functions are related to each other, so you can choose whichever parameterization you prefer. Okay. Good. So this is this parameterization is what I'm going to use in the rest of this talk, but it's nothing fancy. It's just simply related to the one that maybe you're more used to see. Okay. So in general, these gravitational wave backgrounds that can be produced in the early universe can be very different, depending on the source which is producing this background. However, there are some properties which are common across many sources, and you can kind of understand these properties on very general grounds without having to specify a specific source for these primordial gravitational waves. So here I will focus on sources of gravitational waves which are active for some finite amount of time. So they are switched on, they produce this gravitational wave for some time, and then they're switched off. If you have long-lived sources, things are a bit more complicated, and we will see an example of these long-lived sources in the following. But for now, I will focus on those short-lived sources. And for these short-lived sources of gravitational waves in the universe, the power spectrum that you expect to observe is a broken power law. So you're going to have some low frequency tail, then you're going to have a peak frequency, and then a high frequency tail. And you can kind of estimate the location of this peak frequency on very general grounds. So just by dimensional analysis, this peak frequency is going to be located at a value which is given by 1 over some characteristic length scale in the problem. And this characteristic length scale cannot be larger than the Hubble radius at the time at which this source was active, right? So the source is typically casual, so it cannot know what was happening in different Hubble patches. So the characteristic length scale is going to be roughly 1 over the Hubble radius, which is the inverse of the Hubble rate. Okay, this length scale can be smaller than the Hubble radius. So this epsilon star parameter can be smaller than 1, but typically cannot be larger. So this peak frequency is going to be 1 over the Hubble radius, time some factor, which is typically avoided. Now, this is the peak frequency when these gravitational waves were emitted. But as anything else in our universe, these frequencies get redshifted. So the peak frequency that we observe today, which is this F star 0, is related to the peak frequency at the time of emission, which is this F star, by the ratio of the scale factor at the time of emission, A star, divided by the scale factor today, A0. Okay. So now if you express this Abbo rate at the time of emission and the scale factor at the time of emission in terms of the universe temperature, what you find is that the peak frequency that we observe today is going to be roughly 10 to the minus 10, so 10 to the minus 8 Earths times the temperature of the universe when these gravitational waves are produced in units of GeV. So if you want this peak frequency to be within the PTA band or close to the PTA band, you want this source of gravitational waves to be active between, when the temperature of the universe was roughly hundreds of MeV to a few GeV, right? This is the ballpark of the temperature of the universe when your source had to be active if you want to see the background of gravitational waves that it produced within the PTA band, okay? Now, this is just an order of magnitude estimate. This epsilon star value can be much smaller than 1 in some cases. So take this with some grain of salt, but for many models, this gives you kind of a good estimate for where you should expect to see the peak frequency of the spectrum. So what else can we say? Something else we can say on fairly general grounds is what is the maximal allowed value for the amplitude of the spectrum. And this is because these gravitational waves contribute to the energy density which is present in the universe. And the energy budget of the universe is what's driving the universe expansion. So these gravitational waves behave like relativistic degrees of freedom. It's like you had a bit more photons or a bit more relativistic particles in your universe, which are contributing to the universe expansion. So if you have some observables that are sensitive to how quickly the universe is expanding, these observables will also indirectly constrain the amount of energy that you can have in gravitational waves. Specifically, there are two observables that are very sensitive to how much the universe is expanding, and these are Big Bang nucleosynthesis and the emission of the cosmic microwave background. So from these observations, you can set a constraints on the maximum amount of energy that you can have in primordial gravitational waves. So you can set a constraint on the integrated power spectrum of these primordial gravitational waves. And this needs to be smaller than roughly 10 to the minus 6. So 10 to the minus 6, the total energy of the universe can be in these primordial gravitational waves, but no more. And given that these power spectra are typically very peak, you can roughly translate this constraint on the integrated power spectrum into a constraint on the peak amplitude. So roughly speaking, you should expect this peak amplitude to be smaller than 10 to the minus 6. Okay, so on fairly general grounds, we can kind of guess the location of this peak frequency and the value of this peak amplitude. What about the low frequency slope and the high frequency slope? Oh, sorry. Before going to that, if you want to do things a bit more precisely, in this paper they look at these constraints on the total amount of energy in gravitational waves in very detail, and they assume that your power spectrum is some broken power law. So you have a low frequency tail, a peak frequency, and then you have kind of a cutoff. And they derive the constraints on the amplitude of this power spectrum as a function of frequency. These are these dashed line, while these posteriors are the posteriors for the amplitude and the slope derived by nanogram, IPTA, and EPTA. And you can see that if the cutoff is at high frequencies, these constraints on the total energy that you can have in gravitational waves are cutting, essentially already excluding almost half of the posterior region for these parameters. So these constraints, which are fairly general, can really inform quite a bit the posterior for these cosmological sources of gravitational waves. Okay, so we kind of estimated the location of the peak frequency and of the peak amplitude, but what about the slope? So generally, if you want to derive the power spectrum, which is produced by some primordial source, you can compute the anisotropic distribution of energy, which is produced by these primordial sources. And then you can solve Einstein equation to derive the metric perturbation, so the gravitational waves that these produce, right? Now, if you have a stochastic source, you cannot really derive this tensor. But what you can do is to describe it statistically, right? You can derive, again, these 2-point functions for this stress tensor, just like we do for gravitational wave backgrounds. So once you have this 2-point function, you can compute the power spectrum, which is produced. This is just this double time integral of this correlation function. Now, what happens is that when you go on very large scales, meaning when you go at very small values of kappa, so you go on very large scales and things become uncorrelated, right? When you go on length scales which are larger than the Abel radius, all these things are uncorrelated. So you essentially, your process is just a white noise process, and this function goes to a constant value. So this integral here is just going to give you some, it's just going to be some constant value. So the frequency dependence of your spectrum at this small frequency is going to be just f to the cube. So on very general grounds, if you have some source which is acting on a finite time interval in the early universe, when you go to large scales, meaning low frequencies, the slope of the spectrum that you expect to observe, it's just f to the cube. So this is kind of all we can say without having to specify a specific source of gravitational waves about these primordial gravitational wave backgrounds. So we can kind of estimate the location of the peak frequency. We can set an upper limit on the amplitude of the spectra, and we can estimate the low frequency slope. Now, if you want to estimate the high frequency slope or the precise location of this peak amplitude, so the amplitude value, you have to specify a model. You have to specify a source. You have to specify a source that you can use to derive this correlation function for the stress tensor. So in the following, I will look at two specific sources. One is going to be short-lived, so all these estimates are going to hold. And another one is going to be long-lived, and you're going to see that we have some deviations from these general estimates that we were able to derive. So the first example of sources of gravitational waves in the early universe that I want to discuss are cosmological phase transitions. So I think you're familiar with phase transition. You encounter them in everyday life. So if you ever cook some pasta, what you do, you start with a pot of water without the pasta in it. You should put the pasta after the water is boiling. So you start with this pot of water, you heat it up, and what happens is that at some point you form these bubbles of air within the water. These bubbles expand, and the water starts to boil. Now, something very similar can happen in the plasma that was filling the universe very early on. So we talk about this plasma of electrons, protons, and all the particles that you have in the standard model. And in this plasma, something similar to what happens in this pot of boiling water can take place. So suppose that one of these particles in your plasma has this kind of potential. So the initial configuration of this field is such that its value is sitting at the minimum of this potential. But as you cool down the universe, this potential can develop a new vacuum. So your field configuration wants to go from this state to this state. This is just like the water that wants to go from the liquid state to the gaseous state when you heat the pot of water. Similarly here, when the universe cools down, this field might want to go from this false vacuum to the true one. And the way in which the field goes from this false vacuum to the true one is just like the boiling water. You form some bubbles in this plasma within which your field as tunnel from this false vacuum to the true one. And then this bubble will start expanding, okay? And as these bubbles expand, they will collide among each other. They will produce sound waves in the plasma. These sound waves also will collide. And all these collisions can generate very anisotropic distribution of energy, and this can source gravitational waves. But this happens on a finite amount of time, right? You start this phase transition, but at some point this phase transition ends. You convert all the universe to the true vacuum. So this production of gravitational waves, it's active only for a finite amount of time. So we expect all the estimates that we derived in the previous slides to hold. And indeed, the spectrum that is generally produced by this cosmological phase transition is a broken power law with a low frequency slope, which is close to f to the cube. Then you have some peak frequency, which again is proportional to the temperature of the universe at which this phase transition took place. And then you have this scale factor. So this the typical length scale of your problem, which in this case is the typical separation between the bubbles that are formed in the phase transition. And the amplitude of this signal is mainly controlled by this parameter, which is called alpha star, which is the ratio between the energy which was trapped in the false vacuum. You can think about this as the latent energy of your phase transition, divided by the total energy of the universe. So the more energy is released in this phase transition, the more energy is released into gravitational waves. So the louder is your signal. So the stronger is your gravitational wave background. So you have three parameters here. You have the temperature at which this phase transition takes place. You have the typical separation between these bubbles, which are nucleated in the universe plasma. And you have the amount of energy which is released in the phase transition. So now the question is, for which parameters, values, if any, the spectrum that you expect to be produced in this phase transition can fit the signal that we are seeing in PTA data. Okay, so this is what we look at in the nanograph 15-year new physics paper. And this is what we found. So in this plot, I'm showing the posterior distributions for these three parameters. So in this plot, you're seeing two sets of posterior distributions. You have these blue posteriors, which are assuming that the totality of the background that we're seeing is produced by these phase transitions. And then there is this red set of posteriors, in which we assume that the background that we are seeing is some superposition of the signal produced by the phase transition and the signal produced by supermassive black hole binaries. So a couple of interesting things that I think we should notice. So first of all, the temperature that you need for the phase transition is around 100 of MeV. And this is an interesting temperature in terms of the standard model, because this is the temperature with the QCD phase transition takes place. So this is a phase transition that has to take place within the standard model. This is not new physics. This is standard model physics. We know that there must be a phase transition around 100 MeV. The problem is that within the standard model, this phase transition does not produce gravitational wave. This is a smooth phase transition. There are no bubbles which are nucleated. So naively, from this QCD phase transition, you wouldn't expect a gravitational wave background to be produced. But there are modifications of the standard model in which this phase transition can be first order and produce gravitational waves. So it's an interesting coincidence that the temperature that we need in order to feed the signal almost exactly coincide with the temperature which we know there is phase transition in the standard model of particle physics. Another thing to notice is that the strength of the phase transition, so the amount of energy that needs to be released, is very large. Almost all the energy density of the universe at the time of the phase transition had to be trapped in this false vacuum, and it was released in this phase transition. So it's a very loud and a very loud process. So these are the two main takeaways. The temperature needs to be very low close to the QCD phase transition, and the phase transition needs to be very long. But if you have both of these things, you can feed the gravitational wave signal that we are seeing very well. And so really the question now is, which one is the right explanation? It's supermassive black hole binaries, it's a phase transition, or some other cosmological source. And this should be the subject of a different lecture. There are different ways you can go about trying to discriminate between these signals. You can use the different shape of the power spectrum. You can use searches for anisotropies or continuous wave signals, which should be there if the signal is produced by supermassive black hole binaries, but should not be there if the signal is produced by some cosmological source as a phase transition. But this is a possibility. This is a possible source that could explain what we are seeing by producing this background in the early unit. So before moving on, I want to give you a second example. So a second process that can take place in the early universe, which can also source a background of gravitational wave, differently from the example I just gave you of the phase transition. This is going to be a long-lived source of gravitational wave. This is not something that will switch on, produce the background, and then switch off. This is something that will be active on longer time scales. So for this kind of source, the estimates that I just gave you previously won't really hold, okay? So what are scalar-induced gravitational waves? So in this plot, what I'm showing on the y-axis is the power density, the power spectrum of density fluctuation. So we know that in the early universe, there were some tiny density fluctuations, and then these fluctuations in the density of the universe grow and form the structures that we see today, okay? And on large scales, we were able to measure the amplitude of these fluctuations. So we have CMB observations that are able to constrain the power spectrum of these fluctuations in the density of the universe on very large scales. But on smaller scales, we don't really know how large these density fluctuations were in the early universe. So naively, you could just extrapolate this power spectrum that we measure on large scales, so small kappa, to smaller scales, so larger bodies of this kappa. But this doesn't need to be the case, right? There are models that predict that on smaller scale, you have an enhancement of this density fluctuation. So if you zoom in and you look at smaller and smaller scales, these density fluctuations get larger and larger. And the reason why people look at these kind of scenarios is because this is a way to form primordial black holes, which are a very popular dark matter candidate. And the idea here is that if you have these very large density fluctuations on small scales, some of these density fluctuations can get so large that they collapse into a black hole. So you form this population of black holes very early on in the universe, and these tiny primordial black holes can produce a good dark matter candidate. Okay, so this is kind of a cartoon of the process. You have this huge spike in the density of the universe early on very small scales. Some of these can reach some critical density, which here I'm calling delta T, and they collapse into a black hole. And you can kind of estimate the probability of one of these density fluctuations to collapse into a black hole. If you assume that these fluctuations are Gaussian, the probability of reaching this critical density is just the integral of this Gaussian distribution between this critical value up to infinity, right? So if you know the power spectrum of these density fluctuations, you can kind of estimate how many primordial black holes you expect to form in the early universe. And here I'm showing you kind of a realization of these density fluctuations. And here in this, the size of the box is roughly an Hubble patch. And you see that there is one primordial black hole which is formed. What you can also see is that these density fluctuations will form anisotropic distributions of energy and velocities. And these can act like as a source of gravitational waves. So these density fluctuations of small scales can, at the same time, produce these primordial black holes, but also produce primordial gravitational waves. So if you give me the power spectrum of these density fluctuations, I can compute the abundance of primordial black holes that I expect to be formed, but I can also compute the expected power spectrum of this gravitational wave background that they will source, okay? And the relation between the power spectrum of the density fluctuation, which is this P of R, to the power spectrum of the gravitational wave background is given by this relation. So if you give me some power spectrum for these density fluctuations, here I'm assuming it's some peak Gaussian distribution. So you have some peak frequency, K star, you have some width of this spectrum, delta, and then you have some amplitude A. I can derive the induced spectrum of gravitational waves, right? So you have a one-to-one correspondence between the amount of density fluctuations to the gravitational wave background they induce and to the amount of primordial black holes that they should produce. And in this plot, I'm showing this correspondence. So if you want to live, if you want these gravitational waves to live within the PTA band, the typical mass of primordial black holes that this density fluctuation will produce is roughly around the solar mass. So if you have these density fluctuations, and these are producing a background within the PTA band, you will also expect to see some population of primordial black holes of solar mass. Okay, so another question is, first of all, can we feed the signal that we are seeing in PTA data with these primordial gravitational waves produced by these density fluctuations? And second of all, what can we say about the population of primordial black holes that should be associated with this gravitational wave signal? So here, again, I'm showing the posterior distributions for the parameters of the model. We have the peak frequency of the spectrum, we have the width of the spectrum, and we have the amplitude. So you can see that you need a very large peak. So this is the amplitude of the peak, and this needs to be roughly between 10 to the minus 2 and 1. And so it needs to be all the way up here. So you need a very huge enhancement of density fluctuations on small scales if you want to reproduce the PTA signal. Now, there are a couple of other things on this plot. First of all, this gray region. So this gray region is giving you the regions of parameter space, which is excluded by PTA data. So if your model lived in this gray region, you would produce way too much gravitational waves. You would produce a gravitational wave background that we would have seen in previous datasets. So given the fact that we didn't see anything in previous datasets, you can kind of already constrain your parameter space. And what's interesting is that these constraints don't depend on your interpretation of the background. Even if the background is produced by supermassive black hole binaries, these constraints will still hold. And these constraints are complementary to constraints that you can place on these small scale density fluctuations from other observables. Okay, so we are constraining the amount of density fluctuations on very small scale in a way that you cannot do just using CMB data. And these results, again, are independent from the origin of the background. And then there are these green lines. So these green lines show you the region of parameter space in which these density fluctuations produce an abundance of primordial black holes, which can explain the totality of dark matter that we see in the universe. So if you live at the intersection of this green line and this posterior, you are at the same time explaining dark matter and reproducing the PTA signal with the same model, which is kind of cool, okay? After this work, which again was the nanogram analysis, some people look at this in more details. And so there is this paper which appeared this week, I think, by Riotto and collaborators, where they again use PTA data to set constraints on the amount of density fluctuations that you can have in the early universe. So you see essentially the measurements by CMB and Raman alpha at large scales. And then you can see that at very small scales, PTA are the only experiment that can set some constraints. So, and again, these constraints are completely independent from the origin of the background. This is just by requiring that you don't overproduce gravitational waves. And in this other plot, they are kind of showing the constraints that you can set on the abundance of dark matter that can be in primordial black holes, given PTA observations. So the important message here is that, first of all, this model can fit the signal that we are seeing, can produce dark matter. But even if this is not the right explanation of the signal that we are seeing in PTA data, and at the end of the day, we find out that the signal is produced indeed by supermassive black hole binaries, analyzing PTA data allows us to set kind of world-leading constraints on the amount of density fluctuations in the early universe at very small scales, which is something that you can't really do with other observables like CMB and Lamanov. Okay. Good. So this is kind of everything I had to say about these primordial sources of gravitational waves. Of course, the list is much longer. There are cosmic strings, which I think you heard something about this morning. There are domain walls. There is cosmic inflation. The list is almost endless. But the class of sources kind of divides between these short-lived sources like phase transition, which follow all these nice estimates that we can derive on general grounds. And then there are these long-lived sources like these current-induced gravitational waves, cosmic strings, domain walls, and these are much harder to compute the spectrum for. But before moving on, I want to make the point that new physics can appear in PTA data not only via the production of gravitational waves. Think about dark matter. So dark matter is all around us. It's around us at the Earth location. It's around the pulsars that we are observing. It's around the supermassive black hole binaries that could produce the signal. So it's kind of natural to think about the possibility that dark matter can leave some signal in our data. And that is indeed the case, specifically for a class of dark matter candidates which are very light. So if you have a dark matter candidate which is lighter than a few electron volts, the abundance of this dark matter candidate within the Milky Way is so large that you can describe these dark matter particles like a classical wave. So if you're sitting at the Earth location, the usual picture you have in mind is that there are dark matter particles continuously hitting you. But for this very light field, a better picture is to imagine that you are immersed in a dark matter wave. So there is a dark matter wave which is continuously oscillating with a frequency which is set by the dark matter mass and an amplitude which is set by the dark matter. So our telescopes at the Earth location and the pulsars that we are monitoring will all be within this dark matter field, which is oscillating at this frequency, which is set by the dark matter mass. And what people realize is that these oscillations in the dark matter field can leave a signal in our timing data. And the reason is that these oscillations in the dark matter field will produce oscillations in the metric along the line of sight between the pulsars and the Earth. So these beams of radiation which are emitted by the pulsar will propagate through this oscillating metric. So you might have the oscillations induced by gravitational waves, but on top of that, you will also have these oscillations induced by the fluctuations of the dark matter field. And what you can show is that these fluctuations in the dark matter field will show up in your timing data as a monochromatic deterministic signal. So you will have a deterministic signal, which is this h of t, which has an amplitude which is set by the dark matter of your field, this rho phi. And the signal is oscillating at a fixed frequency, which is set by the dark matter mass. Okay, so this is very similar to a continuous wave search. In general, you're going to have different correlations in the signal of different pulsars, but the fact that the signal is deterministic and monochromatic, it's kind of something that's in common between the two kind of searches. So people realized that you could search for these kind of signals kind of a long time ago. And I think the first search for this ultralight dark matter signal was carried out by the Parks collaboration in 2018. They didn't find any evidence for this monochromatic signal, and that allowed them to set some upper limits on the density of dark matter within the Milky Way. And these upper limits are shown in this plot with this black solid line. And this can be compared with the local dark matter density that you expect to have within the Milky Way. And these are these dashed horizontal lines. So you can see that the upper limits that they were able to place couldn't really test the dark matter density that you expect to have within the Milky Way. Okay. But the situation has improved a bit. And these are the results for the same kind of analysis by the nanograph collaboration and the EPTA collaboration. So especially for the case of the EPTA collaboration, you can see that the upper limits on the dark matter density that they were able to place go below the expected local dark matter density. So essentially, the fact that they didn't see this signal in their data allow us to say that if the dark matter is made of this ultralight field, they cannot have a mass between 10 to the minus 24 and 10 to the minus 23 eV. If they had a mass in this mass range, we would have already seen the signal that they are expected to produce in our data. Okay. Now, if you look at these plots, you probably will see two features, roughly around 10 to the minus 23 eV. And this is kind of this value for the dark matter mass corresponds to a frequency, which is the frequency of the monopole that we kind of see in both EPTA and nanograph data. So in a sense, if you really want to believe that this is the case, you could think that the monopole that we are seeing with very low significance in our data could be produced by some kind of ultralight dark matter signal. Now, these values for the dark matter, so dark matter masses around 10 to the minus 23 eV, are already very strongly constrained by other astrophysical observables because such light dark matter candidates will suppress structure formation. So it's really hard to explain the monopole in terms of an ultralight dark matter signal, at least if you assume that this field couples to the standard model only via gravitational interactions. If you take some more exotic models where these fields couple directly to, say, electrons, you could do that. But again, this is a bit of a very exotic explanation for the monopole, but this is something to keep in mind. Okay, so far we have discussed primordial sources of gravitational waves. We discussed some specific examples. We discussed some of the general properties that they should have. We discussed some other kind of neophysics signals that you might have in PTA data, which are not tied to a gravitational wave signal. And this is, for example, the case of this ultralight dark matter signal. There are other cases of signals that can appear in our data and not being of gravitational nature. You can have some dark matter substructures running around the Milky Way, and this can also produce a signal. So there is a very large class of models that could give a signal in our data. So a lot of people in the community are interested in testing their models against PTA data. So what we did to kind of facilitate this work and to allow people to really analyze real PTA data with proper statistical tools, and also kind of to make our life easier when we want to analyze a large class of models, is to develop this code, which is called PT Arcade. You can find more information at this documentation page. So this code is nothing fancy. It's just a wrapper of Kefil and Enterprise. But what it allows you to do is to analyze PTA data without having to know how to use either of these two analysis tools. So you don't need to know how to use Enterprise. You don't need to know how to use Kefil. You don't need to know what is a PTA likelihood. You don't need to know where to get the data, the noise data, and so on. So how does it work? So in general, if you have some new physics signal, this is either stochastic, like a gravitational wave background, or it's deterministic, like the signal produced by ultralight dark matter. So your signal is going to be specified either by the power spectrum of your gravitational wave background or by some time series of your deterministic signal. This is all you need to specify, all you need to know to specify your model. Okay. So the goal of PT Arcade is that you specify your model either by giving the power spectrum or by giving this deterministic signal. And PT Arcade will give you, like magic, the posteriors for the parameters of your signal. So let's try to look a bit under the hood of how this works. So you start by installing PT Arcade, and we will see how that works. And when you install PT Arcade, it automatically downloads all the PTA data from Nanograph, IPTA, and soon also ePTA. And by all the data, I mean all the pulsar files, all the noise files, all the empirical distributions. Then PTRK takes your model that you have to provide via some model file and implements your model in the PTA likelihood, either in Enterprise or in Kepler. Then takes this PTA likelihood, it defines some sampler, starts an MCMC chain, and what it gives you are the MCMC chains. So the user only has to specify this model file where it specifies the signal that he's trying to look for. And at the end of the day, you will get these Monte Carlo chains that you can use to derive the posteriors for the parameters of your model. So this is a very simple architecture. So let's see how you can actually use PT Arcade, going from how to install it, how to write this model file, and if you want, how to fine-tune some of the details of the runs. So installation should be very simple. If you're using if your Linux machine or iOS with Intel chips, it's just a simple common install. You have to work a bit harder if you're using a Mac with some silicon chips, but it should be a one-line. Okay. And this installation, again, takes care of also collecting all the data that you need to run the Monte Carlo chains. So you just have to run this line of code and you're ready to go. Okay. The second step consists in specifying your model. This model, again, can be either stochastic or deterministic. Here, I will consider a stochastic signal, so a gravitational wave background signal. This signal is specified uniquely by the power spectrum. So here, I'm assuming that your model has some broken power low spectrum. So you have a peak amplitude A star and some peak frequency F star. So you, in this model file, this is a simple Python file, you have to include two information. First of all, you have to include the priors for your model parameters. And you can do so using this parameters dictionary. So the keys are the names of your parameters. You can choose whatever you want. And the values of these dictionary entries are the priors that you want for these parameters. So you can look at the documentation, but you can choose from some predefined set of priors, uniform, log uniform, exponential, and so on. Okay, so you specify the kind of priors, you specify the prior range, and you're done. The second thing that you need to specify is the signal function. This, again, it's either the power spectrum, if you're looking for a stochastic signal, or the time series of your deterministic signal. In this case, we have a stochastic signal, so we have to define the spectrum. So you have to define in your model file a spectrum function. The first argument of this spectrum function needs to be an array which contains the frequency at which the code will evaluate the spectrum. And then you're going to have whatever model parameters you have. In this case, you have A star and F star. Okay. And this spectrum function needs to return the value of the power spectrum for each value of the frequency and the model parameters. Okay, so this is all you need to define in the model file, and in principle, you are ready to go. Okay, this is all you have to do. Define the priors, define the power spectrum, you feed this into PTRK, and you're gonna get the posterior for the model parameters. Now, if you want to be fancy, you can also specify additional properties of your signal. Say you have some very fancy physics model that produces some stochastic signal with some modified overlap reduction function. You can define your modified reduction function. You can define this function. This is going to take as arguments the frequency, because you can also define some frequency-dependent overlap reduction function. You're going to take the position of the pulsars, and then whatever parameters you want to have in your model. So this overlap reduction function can depend on the frequency and can depend on the parameters of your model. And this is particularly useful if you want to look for some modified gravity signals in which the overlap reduction function is modified. And then you can also specify the name of your model. This is just used to save the output. And you can specify if you want to overlay to the signal from your model, also the signal from supermassive black hole binary. So you can produce a signal which is kind of the superposition of these two sources. Okay, but this is all optional stuff, right? The only required content of this model file is the priors that you specify via this dictionary and the power spectrum. That's all you have to include in this model file. Once you have the model file, you're ready to run the code. You call PTRK, you pass the model file, and you're done. You just wait. If you're running using CAFFIL, you have to wait just for a few minutes. If you're running using Enterprise, you probably have time for a coffee or even more. But then the output is going to be the usual output you are used to see from an Enterprise or CAFFIL run. They're going to have some output directory that you can specify. Inside this directory, there is going to be a folder with the name of your model that, again, you can choose. And then you're going to have the chains, the parameters, the prior, the usual stuff that I think you're already used to see when you run Enterprise or CAFFIL. Okay. And once you have the chains, you're done. You can do the posteriors. You can do whatever analysis you want to do. Okay. So it should be very straightforward. A lot of people outside the PTA community have been using this. So, and these are people that have no idea of how actually implement a PTA analysis. So it seems to be working. Now, what I told you so far, this model file and so on, it's the fundamental piece of information that you have to provide to PTRK. But you can also provide additional information if you want to fine-tune your runs. And you can provide these additional informations using a configuration file. So when you run PTRK, you can also pass an additional file, this config file, where you can specify more details about the run. For example, you can choose, again, if you want to run using Enterprise or CAFFIL. So you just have to define this small parameter, and you can either choose CAFFIL or Enterprise, and that's going to decide which one of these two tools you actually use under the hood. You can specify the PTA dataset. Say you want to analyze your model across different datasets, you can just change the dataset and also the PTA likelihood that's defined under the hood with different noise parameterization and so on with one line. So you can switch between nanograph, ePTA, IPTA, and the corresponding noise models with one line, which is kind of useful. You can specify if you want to include or not the cross correlations. You can decide how many frequency components you want to keep for the gravitational wave background. You can specify how many frequency components you want to keep for the intrinsic red noise. You can decide if you want to resume some old runs that you stop or not. You can decide where to save the chains, how many samples you want, and so on. Then you can decide if you want to do a model selection run. So if you want to compare your new physics model with the SMVHB model, which within Enterprise is parameterized in terms of a power law, so you have some amplitude and slope. And you can fine tune the priors for these astrophysical parameters. You can use some theory priors. So if you set these theory priors to be true, the priors for these parameters are going to be derived by fitting a 2D Gaussian to the posterior values of these parameters that we derive using ODEC. Otherwise, you can use some more generic uniform priors. That's up to you. So these are all optional parameters that you can play with and you can use to kind of fine tune your runs. Now, this has been developed to help with the search of new physics models, but it's not really, it's not like it can be used only for new physics. If you have some whatever signal with some power spectrum, and for example, you want to test it against different PTA datasets, nanograph, ePTA, iPTA, and you don't want to waste time changing the noise models and so on, you can use PT Arcade to easily switch between different datasets. Okay, that brings me to my conclusion. So yeah, we have this strong evidence for the presence of a gravitational wave background. If this background is of cosmological origin, it will provide the first direct glimpse into the dynamic of the universe very early on, fractions of a second after the Big Bang, which is something we cannot do using electromagnetic radiation. Only gravitational waves can provide a window into these early stages of the cosmic history. Independently from the origin of the background, even if the background ends up to be produced by supermassive black hole binaries, we can use PTA data to set very strong and complementary constraints on a large number of new physics models. And finally, I show you that if you have some model that you want to test against PTA data, you want to do it quickly, you can use PT Arcade. It should be easy. You can find more documentation on the webpage. So, and if you have any doubts or you want to contribute, please reach out to me and we can discuss. Yeah, that's all I had. Happy to take questions.
Thank you very much, Andrea. Do we have any questions? You're all just amazed at the different variety of cosmological signals that can happen.
Yeah.
Yeah, that is very comprehensive. So all of this might be alongside or just lurking underneath the supermassive black hole binaries for us to find. I can't see any burning questions right now, but I'm sure Andrea would be happy to answer any questions if you put them in the Slack later on. So with that, thank you very much again, Andrea. It was really fantastic.
Yeah, no problem. It was a pleasure.
Okay, everyone. Well, now we can move into lunch. We've got pizza today, which is at the back of the room. So there's a kind of different stacks of pizza. I haven't looked at what it is. We've also got, I think, salad, and then there's a pizza box full of cookies as well for you to try. So help yourselves. We'll come back at 2 o'clock. Hey, Polina, we'll come back in about 5 minutes or so. There are people still having some lunch.
Okay, yeah, no worries.
But thanks for the advice.
Okay, everyone. Let's get started back for our final tutorial session. Hopefully you've fully digested that pizza. I'm still kind of working on mine. But Paulina has an exciting follow-up to yesterday's continuous wave search to let you know about. And I think there are some brief installation instructions to help you make some sky maps that Paulina pasted into the Slack. So without further ado, thanks, Paulina, again.
Yeah, happy to see you all again today, even if it's virtually. So there's a few kind of like setup things that we need to get started with. I think, so I have a pull request for the repo, which has all of the materials that you'll need for today. So I think we might need to take care of that first, and then you all will just need to grab it. So I don't know. Just let me know kind of once that is taken care of.
I just purged it.
Okay, great. Thank you. So yeah, if you all just want to pull that those materials from the repo. And then one other small kind of setup thing that we'll need to get started is, let me share my screen. So in this CW tutorial 2 directory, you'll need to copy and paste that same example chain that we were working with towards the end of yesterday's notebook. So it should be under your day 4 tutorial CW tutorial directory. Just take that example chain and then paste it into this directory as well, because we're just gonna use that throughout the rest of this notebook. So I'll give you all a second to do that, and then yeah, at the very beginning of the notebook as well, follow the instructions in this link here to get ligo.skymap installed. I think pip install is probably just the easiest way to go about this. I think it shouldn't really have any issues, but I'll just give y'all like a minute or so to get all of that set up. Yeah, so the exact file name is example chain .h5. It's that HDF5 file. And then that will go in this directory here. All right, how are we doing in terms of getting things set up? If y'all want to just put a thumbs up in the air if you have the materials pulled, LIGO.SkyMap installed, and the example chain in the directory.
Any problems anywhere? I think we might need just another few minutes, Paulina.
Okay, sure, yeah, no problem.
Paulina, could you magnify your notebook a little bit, just so people in the room can see?
Sure, let me do that. How's that look?
Yeah, that's much better. Thanks.
Better? Okay.
Any problems with setting from the repository to the filter, to the materials, getting like the scan out and so. Fixing period.
Just for me to keep track of time as well, this session ends at 3:15, right?
Yeah, if we could wrap up, but if you go over, that's totally fine. But
Okay.
there's no scheduled session after that. It's just really a wrap up and talking about open questions in the field after that.
Okay, cool.
Still some installation problems, maybe.
Oh, yeah, I'm just figuring out how to change.
Yeah.
Or like to move it from having downloaded it into the right.
We should put it in the directory.
Yeah.
Where is the other one? Chief. What's in your? Yeah. What's that? So then if you opened up your terminal, just download So we're still in the room getting the chain file into the same directory as the tutorial to make sure it can be read in.
Okay, okay. Yeah, that makes sense. It's a kind of big file, so. If you have gotten to the point where you have everything successfully set up, feel free to go ahead and just read in the import statements and then setting up the base directory. And even going so far as to read in like these this data set that we were working with yesterday and also the chain files so that we can have that all set up.
Yeah.
Where does it meet? So I think sample. Then you go through probably start I think like one of the big active. Yeah.
Is there anything that people have encountered that would be useful to share with the entire room about paths, perhaps?
I think maybe five samples and then drop in the same location that is located.
You change the name of it to samples?
So like if you go to the notebook, it's I guess examples. Change the name to samples, .85 should work.
Okay, so in the room, Kyle is saying if you change from example chain to, huh?
I have it changed. I just dropped the file in like the main.
Okay, so it could also work just with taking example chain .h5 and dropping it into the same folder as the notebook.
Example space the example
Does it seem like the underlying issue is just in copy and pasting it or in actually reading it into the notebook?
Fine. I have a problem.
So it seems to be in finding it after doing the download,
Okay,
but it should be just in your tilde downloads folder.
I also just put it in the Slack. If people do that.
Oh, okay. Thanks, Mercedes. Mercedes had put it in the Slack as well.
Okay, great.
Yeah, it seems to be working now.
Okay, so how are we doing in terms of just reading it in?
Is reading in okay now? Thumbs down if you haven't been able to read it in. Okay, so Yashvi, Nikita, and is that a... So Nikita, you had the Lego.SkyMap problem, but is that separate from reading in the chain file?
Yeah, I'm not able to solve that. Like, we'll go to.
And Yashvi, are you having problems installing Lego.SkyMap as well?
I can't find the chain, but.
So the chain file, if you go to the school Slack, Mercedes put it in there, so you should be able to just download, put it into that directory. Okay, so now the issue is just installing Lego.SkyMap. Okay, so maybe I'll come over and we can just brainstorm. But Paulina, I think otherwise you can go ahead. I think most people have been able to read in that chain file.
Okay, great. So yeah, I think to kind of give you an overview of what today's tutorial is going to involve. So we kind of really rushed through really quickly yesterday, starting to look into specifically the sky localization that we can get from a continuous wave analysis. So this notebook today is going to be all about kind of looking at the sky localization, plotting it in a number of ways, even just getting familiar with some plotting tools, using a few different packages, and then starting to look at how many potential host galaxies we might have in areas of this size, and then how we can even try to cut down on that number. So I think in terms of walking through it, it'll be pretty much the same format as yesterday. We'll just walk through it together. I think I did not do a great job yesterday of realizing when there were lines for you to fill things in. So I'm going to go through the same notebook that you see so that I can see whenever those fill in the blank parts come up, give you a second to fill that in, and then switch over to the tutorial solution version so that we can see what that looks like. But yeah, so go ahead and read in all of the import statements if you haven't done so already, and the base directory, as well as the simulated data set and the chain. And then so for looking at the sky localization, we're just going to need the samples for cosine theta and phi. And then I just kind of stack these all into their own little mini chain of sky samples. So the first thing we're going to do is just see how well our continuous wave analysis did in picking up the right sky location. So I have the true sky location here, and then we're going to plot a quarter plot, and that should look a little something like this. So you can see it recovers the sky location pretty like smack dab in the middle of the posterior distribution. So that looks really great. And I would say this is kind of an ideal case as well. Maybe sometimes the localization is a little bit off. We might have the injected value, somewhere within this 68% credible region contour, or even lying in the 95% contour outside of it. But that is still pretty good. So just getting a sense of what this looks like, then let's go ahead and actually plot it on the sky and see how big of an area this looks like when we look at it on the sky. So for this, we're going to use HealPy. So HealPy, it uses this hierarchical equal area pixel scheme. So it basically splits the sky into equal area pixels. And you can actually, let me bring up a few images to show you what this looks like. So It basically kind of subdivides the pixels by 4. So the lowest number of pixels you can have is 12 across the sky. And so if we kind of unraveled the sky map into just this rectangular map, this is what it would look like. So these pixels are numbered 0 through 11, so 12 pixels. And then for each pixel, if you wanted to go a resolution higher, then it would subdivide each of these pixels by 4. And so then you'd get a different indexing scheme based on the new number of pixels. And then I think this is yet another subdivision here if you wanted to go even another resolution higher. So you can just see how it gets more and more fine-grained as you go up to higher resolution. And if we wanted to see what this looks like in spherical format as well, we have some images here. So again, starting with, the highest or lowest, I should say, resolution of 12 pixels, and then subdividing it by 4 every time gets you kind of narrower and narrower in terms of resolution. So that's kind of the software package that we use typically for plotting our sky posterior. So this resolution parameter we call n-side. So you can choose n-side values that are powers of 2, with the lowest one being 1 and then going up. And then the total number of pixels is this little formula here is just 12 times n-side squared. So for an n-side of 1, you have 12 pixels and so on. Typically, I would say we tend to use a resolution of n-side of 8, which is 768 pixels. So that's pretty much what we're going to stick with as our standard throughout this tutorial. So to make an actual sky map from our sky pixels or our sky posterior samples, we're going to use this function that I've created here, and I'll walk through it a little bit. And then if you want to take some time later to actually, go through step by step, print out what each step is doing, I think that would be helpful to kind of actually get a sense of what this function does. So the very first thing is this function here, n-side to npix, just gives you the number of pixels for the given resolution. And then based on the resolution that you choose, you're going to use ang to pix, so kind of angle to pixel. You need to give it the resolution because, different resolutions will have different pixel indexing. And then your theta and phi samples. So each of these samples is going to be assigned a different pixel index. So basically this function is going to go through and, take a certain posterior sample and find which pixel it falls into based on the resolution that you've chosen. This here is going to then kind of just go through and count up how many of your samples fall into each pixel. And then here we're actually just creating a blank sky map. It'll be blank with an array that is the same length as how many pixels you're going to have. So in this case, we're going to have a 768 length array. And so then for each of those indices, that will correspond to each pixel index, and it'll populate each of those indices with the number of posterior sample counts in each of those pixels. So go ahead and run that function and then make the sky map from the posterior samples. This will take theta and phi, so you'll need to kind of convert cosine theta samples to theta samples, give it the resolution as well, and then run the following cell after that as well, and you should see something that looks like this. This is where mine looked a little bit messed up yesterday. I think it was because I didn't actually have the chain or something along those lines. So this is what your HealPi map should look like. The way that we do this plotting is just to use this function here, which is a mol-wide projection. Mol-wide is pretty standard. This is also an equal area kind of projection scheme. So people use it pretty typically when they're plotting, images of the sky or of the world. And this is also, you can see some kind of pixel scheme here too with all these circles. So it's just an equal area projection. And then this function here, proj scatter, that is used for any kind of just individual points that you want to plot. So here we're plotting all the pulsars in light blue. And then here we're using it to plot the actual injected location. And then HealPy is a little bit weird whenever it comes to plotting axes labels for whatever reason. So here we just did it by hand. So that's kind of just handy if you need it at some point later. And then this line here is just plotting all those grid lines so that you can more clearly see where everything is. All right, and so you get this sky map here with the most dense pixels in yellow, and then the ones that don't have any points in this dark purple. So we can see the densest pixel here is actually pretty close to the injected value. And I mean, the injected value really just falls in like this area where we have our densest pixels, which is great. And we already kind of saw this as well with our corner plot earlier. So from here, I'll give you guys just a second. Feel free to go up back where we set the resolution. So in this line here, and change this n-side value to lower or higher. So changing it lower will lower the resolution and making it higher will increase the resolution. So remember, you can choose powers of 2. So play around with that a little bit. I'll give you guys a minute or so and see how this map kind of changes and how fine-grained it looks. All right, so I'm gonna go ahead and change this to n-side of, I don't know, 64 or so and see what that looks like. Yeah, so you can see that gets really pixelated kind of really quickly. If we even go maybe from n-side of 8 to 16 or so, just bump it up by 1 level. That looks okay. I feel like that looks pretty good. Sometimes you kind of have to be careful in terms of the resolution that you choose, because sometimes our posterior samples are just not so kind of like constrained enough that going up to higher and higher resolutions is going to be helpful. So like we saw for the n-side of 60 or the n-side of 64, it really didn't really look very informational at all. It kind of just gets into the weeds and becomes really diffuse looking. But if you change this n-side value, played around with it, go back and change it to an n-side of 8, since that's kind of what we'll stick with for now. So make sure your map looks like this before you move on. And then maybe something I didn't note here as well is this color bar is just showing you how many posterior samples are in each pixel. So for this densest yellow pixel, for example, we have about 150,000 samples. Another thing we can do instead is to normalize the counts, so then we can actually see the density of pixels as our color bar. So that's what we're going to do here in this next cell and then replot. All right, and so then you should get something that looks like this. So we have about 15% of the posterior samples in this densest yellow pixel, and then the ones around it are a little bit less dense. Some other HealPy tools that we can use, I'm just going to kind of get you familiar with them and see what kind of questions you can answer. And I wouldn't even say even questions, but just little tools if you need to know, for example, which pixel corresponds to which sky location and vice versa. Or, you know, if you choose a specific resolution, what is the size of one pixel exactly, and that kind of thing. So let's run through these next few cells here. So for this first one, we're going to use this this function called HP pix to ang. So I feel like typically HealPy does a good job in almost telling you what the function does in the function name. So pix to ang will be pixel number to the actual angle value. So what is the sky location for a given pixel? So here we're going to use an n-side resolution of 8 again, and then just as an example, what is the sky location for a pixel number of 123? So again, you'll need theta and phi coordinates for this, and then to actually convert those into a right ascension and declination, which you might be more comfortable with, we'll use this numpy radians to degrees function, and then we can see that this corresponds to this RANDEC here, both in degrees. In the reverse scenario, you could ask, you know, for this specific right ascension and declination, which pixel number does this correspond to? And this is kind of what we already did whenever we created our sky map. We had theta and phi samples, and you know, this ang to pix function took all of our samples and then assigned them to different pixels. So if we go ahead and run this, we can see that this coordinate corresponds to pixel number 193. And again, if you choose a different n-side value, that pixel number is going to change. So just be careful of that. And then something else we might need for the future is just to see what the area of one pixel is for this n-side resolution. And for this, we can use n-side to pix area. So go ahead and run that, and you should see an area of about 54 square degrees. All right, so now with some kind of tools on our belt and having a visualization of what our localization area looks like on the map, let's go ahead and do a little bit more calculating to really get some information from this sky map. So the very first thing we're going to do is create a credible level map. So we just created just like a counts map to see how many posterior samples fall into you know, each pixel. Then we normalized it to see the density. And now we're going to create a credible level map from our density map. So what this is going to tell us is basically what percentage of you know, of posterior samples fall within you know, a given credible level. So for example, if we wanted the 95th percent credible level, this is going to be kind of like that central region like we had in our corner plot here. This outer circle here is corresponding to the 95th percentile. So it's that kind of like innermost 95% of posterior samples. And then if we wanted to go narrower for a 68% credible interval, we could do something like this. So taking the 95th percent credible interval as kind of our standard here, we can use this little algorithm to create a credible level map from our density map. So first, we need to sort the pixels by descending probability density. So we just assigned a probability density to all of our pixels, the most dense one being about 15% or so. So we're going to start with that most dense pixel and then work our way up, adding on you know, the next densest pixel and so on to see you know, which pixels fall within a given percentage. So after that, I kind of just explained this step already, but then we're going to cumulatively sum, from 15%, and then maybe the next pixel contains 5% or so. So that'd be a cumulative sum of 20%, and that would be kind of like your 20% credible level. But we're going to sum up all the way through all of our pixels and then put them back to their original order so that we have each pixel assigned kind of what credible level they fall within. So I have this little recipe here for you within Python already. And then this is what you should see. So this again is corresponding to each pixel index, and then we can see a lot of them have ones. So a lot of them are really just not very dense with samples. Maybe they don't have any samples at all. In fact, I think all of these ones that have ones don't have any samples, and so they don't contribute to the credible level at all. But yeah, this is kind of what they look like. And just to note that, we have our density map and we have a credible level map, and they're kind of opposites in a way. So the most probable pixel is going to have the smallest credible level. So for example, our densest pixel of about 15% or so, that's going to be the smallest credible level that we can work with. And then as we work our way up, for example, to like credible level of a 99% or so, those are going to be pixels that are not quite as dense because they don't really contribute as much to the total credible level. I know that might be a little bit confusing, so if you have questions, we'll stop in a little bit and feel free to ask. All right, so kind of the standard in terms of credible levels is looking at the 90% credible region for sky localization. So that's what we're going to use here. So this is just the area in which 90% of the posterior samples fall. So we're going to just first off pick a number of different pixel indices and check if they fall within the 90% credible region. So all we have to do here is just pick a pixel index and then check whether inside the credible level map, if its credible level is less than or equal to 90%. So feel free to run this. We can see for this example of pixel number 123, which we worked with earlier, it does not fall within the 90% credible area. Try out some different numbers here, and then I will also pause here for any questions that we have up until this point.
Paulina, can you explain what a credible level is again?
Yeah, sure. So the credible level is basically kind of almost like the central region where your posterior samples fall. So if you wanted a credible level of 68%, that's kind of like the same, or not the same, but analogous to a confidence interval. So it's kind of like a 1 sigma standard deviation, but for Bayesian statistics, if that makes sense. So up in this corner plot that we had, if you wanted the 68% credible level, that would fall somewhere in like this edge and then this edge. So like on either side of where like the peak is. And then as you kind of expand that credible level, so say 95% credible level, that will be even further. So you're kind of just taking the central percentage of points.
Okay, so does that mean like a smaller credible level is like a more accurate distribution, or like a
I don't know if I would say more accurate, but just kind of taking a smaller chunk, I would say, of the distribution. Yeah. Yeah, because we could have, recovered this kind of offset. So if you took the 68% credible level in this case and it was offset from this peak, you might run the danger of kind of cutting out that the true kind of like value that we injected, if that makes sense. So I don't know if I would say more accurate, but definitely just kind of like a smaller piece of the distribution. Yeah.
Okay, thank you.
Yeah. All right, so hopefully you've had a chance to just play around with this a little bit and pick some different pixel numbers. And yeah, I think that's about it for this. Something else you could try is to just try a different credible level value. So for example, you could take the 50% credible level. So it would be kind of like the 50% sliver in the distribution. Yeah, give that a try if you haven't yet. And then we'll start to move on to some other calculations here. So the next thing we're going to do is look at, which sky location is the most probable. So we've kind of seen this already with like that yellow densest pixel. So we already have a sense of where this is, but if you wanted to get a value for which sky location actually corresponds to this pixel, then you can use a few different tools that we've already looked at with HealPy. So I'll give y'all a second to fill in some of the functions and things in here to find the sky position of the densest pixel. And then as well, since the pixel kind of encompasses our small size of the sky, it's not quite, a pinpoint region, but like we saw for inside of 8, for example, the area of 1 pixel is about 54 square degrees or so, which is still pretty big. But if we want to see, what's the probability per square degree within that pixel, we can use another inside to pix area calculation here, and then take that. Sorry, I kind of just lost my train of thought. We can find the probability density and then divide it by the area of the pixel. So I'll give y'all maybe a minute or so to fill these things in, and then I'll bring up the solution notebook so we can take a look. If you happen to kind of finish up with this early as well, feel free to move on to the next cell. The next cell is going to walk you through how to calculate the area of a credible region. So again, we're going to use our 90% credible region, and how we can do this is just to count up the number of pixels that fall within the credible region, and then multiply that by the size of 1 pixel. So feel free to go ahead and run that and kind of sit with it, think about it a little bit if you'd like. All right, I'm gonna go ahead and pull up the solution notebook here. So for this, you're gonna need your normalized sky map. And then you'll need to convert your resolution and then the index of that densest pixel to coordinates here, theta and phi coordinates, and then convert them to ARIA and DEC coordinates, and that will give you the sky location for the densest pixel. And then to find the probability density per square degree for that pixel, we can use, again, our normalized map, take the index of that densest pixel so that we have our probability density, and then take the probability density and then divide it by the area of one pixel. So again, using this n side to pix area function, and then we'll get a probability density of 0.002 per square degree for this map and for this resolution. And then if you have or haven't moved on to this area cell here, so we're using our 90% credible area, and I have kind of printed out here what the almost like true credible level is here. So kind of like I mentioned before, our densest pixel has a density of about 15% of the posterior samples. And then if you were to add on the next densest pixel and say it contained 5% of the samples, then you'd have a cumulative sum of 20%, and that would be your credible level of 0.2. So you can see how they kind of jump discretely. They're not quite, like 15, 16, 17%. So you'd go from a 15% credible level to a 20% credible level. This gets a little bit more fine-grained once you're working with higher resolutions. But just so that you can see exactly what the credible level is for all of those pixels that you summed up for a 90% credible level, it's pretty close, 89.9%. And then the area of this credible region is about 860 square degrees, which is pretty massive. So again, I just have like a space here for y'all to explore some things. Try a range of credible levels and calculate the localization area for each. You can also, for this range of credible levels, plot what the area looks like as a function of the credible level. You might encounter this error, and that is, again, going to be due to the fact that you might choose a credible level that falls below 15% or so, since we don't have any pixels that kind of add up to the 15% credible level. So just kind of be aware of that. Try not to, use any values below 0.15. But if you had a different sky map, for example, that, the densest pixel held 5%, of the posterior samples, in that case, you could go to lower credible levels. So yeah, I'll take a few minutes here as well, try some credible levels, calculate the areas for those, and then plot them. And let's take maybe about like 4 minutes or so. And of course, if you have any questions, feel free to come up. All right. Let's, for the sake of time, move on a little bit. So let me bring up kind of what my notebook looks like. So I just went ahead and picked a range of credible levels, 100 values between 0 and 1. So basically, 1, 2, 3, 4%, et cetera, except for those that lie below 15%. And if you kind of plot what those look like, those areas as a function of the credible level, you might see something like this. So I think kind of as expected, as you kind of look at kind of larger and larger portions of your sky posterior, you'll see larger and larger areas. So really kind of just increasing, and then this really just shoots up to kind of the I think entire sky, just because you're encompassing, when you're at 100% credible level, you're encompassing all of your posterior samples, and they span the entire range of the sky. So that's why this point kind of jumps up here, but typically you'll see a pretty smooth progression of your area size with the specific credible region that you're looking at. Now let's get a little bit more into some of the fun stuff. So I'm going to introduce you now to LIGO.SkyMap plotting. So this is kind of switching gears a little bit. Instead of using HealPy as our SkyMap plotter, we're going to use LIGO.SkyMap. So this is the SkyMap visualization software that LIGO uses for their gravitational wave events. And it has a lot of really cool functionalities with plotting and stuff that we'll get started with in this notebook. And I have some links here as well for you if you're interested in looking at other things that you can do with it. But first, let's go ahead and just plot the 90% credible area that we calculated earlier with LIGO.SkyMap. And you should see something that looks like this. So we're using kind of that characteristic orange 2D histogram kind of distribution that LIGO uses as well, if you've ever seen what their sky maps look like. But we've also got this nice black contour here that just outlines that 90% credible region really well. And all of these stars I have here represent the pulsars that were used in this simulated data set. And then this white diamond shows the actual true injected sky location. So you can see here as well that we do pretty well in recovering the right sky location. Take some time now to play around with this. This might help you visualize the credible regions a little bit better. You can kind of copy and paste this block of code and just change the credible region value that you're using. So go ahead and you might need to kind of copy and paste some of the things up here as well to calculate whatever credible interval you're interested in looking at. So I might suggest maybe like 50% or 68%, 95%, play around with it a little bit, and we'll take a minute or so to do that. I guess it'd be helpful as well for me to walk through what this block of code does a little bit more. So to set up our axes, we use the mall-wide projection again. Luckily, LIGO SkyMap has a really kind of great projection parameter here that we can use that sets up kind of the orientation that we like to use in astronomy. So this astro hours orientation here. This line here is actually plotting that 2D histogram of our posterior samples. And then this line here is plotting that black contour that we saw. So something important that's needed for this is we need to set the kind of level that we need for the contour. And to do that, I have this line up here. So this kind of finds like that index of the true credible level. And we need that here for this levels parameter. And again, we're using this density version map, so the normalized sky map. And then the other few things I have here are just plotting the pulsars and then the injected location. Something important that you'd need for plotting scatter points, if you're plotting in rate ascension and declination, you'll need this parameter here, which transforms these coordinates to the axes coordinates. And then if you wanted the grid, of course, we have the grid function here as well. So whenever you plot a new credible level, for example, you'd need to go back and find what you'd need for this level parameter, for example. So you need the normalized map, and then you need the index of the credible level that you're looking for. So for example, here where the credible levels are falling within the credible level map values are falling within the level that you'd like. And then this index here is just finding where the maximum kind of value of that credible level map is. So that's what you need here for this levels parameter. Hopefully, kind of while I've done all that talking, you might have plotted another credible region or so. You can also just kind of look at what I've got in the tutorial notebook or copy and paste it and change things as you'd like. But I plotted, for example, the 50% credible region, and so we can see what that looks like here. Again, it's not exactly the 50% credible region because we have kind of that discreteness going on with all of our pixels. So this is about like the 44% credible interval, and this has an area of about 215 square degrees. So smaller as we might expect. But this also lets you visualize kind of what that difference is in the 50% credible level here versus the 90% credible level here. All right, so having done that, it's time for us to actually start looking for some host galaxies. So this is a little bit of the fun part, but also a really huge challenge. So we have this area of about 800 square degrees for the 90% credible region, and that's a pretty big chunk of the sky to start looking through to find where our gravitational wave signal actually came from. So how do we begin to tackle this question of, where the gravitational wave signal came from, which galaxy it came from? If we have, a list of galaxies, for example, how can we try to match up, the signal with the correct galaxy? There's a number of things that make this challenging. So like I just mentioned, we have a huge region. In regions of this size, PTAs are not really well known for their localization capabilities. We expect that when we first start to detect continuous waves, we'll have areas on the order of hundreds to thousands of square degrees. And in sizes, areas of this size, you might have galaxies on the order of also, hundreds or thousands of potential galaxies. And you can't really go through and point a telescope at each one of those galaxies in that area to see if you could find, for example, a potential electromagnetic signature like some of the ones that Maria talked about this morning. It's really not feasible to be looking at that many galaxies, for an observation campaign. So that is a challenge, as well as, Maria talked about this variety of electromagnetic signatures that we might see from these systems, but we only have indirect evidence of these systems. We don't have any direct confirmation. And there's a lot of ambiguity that surrounds some of these electromagnetic signatures. Some of them might even be created by just one supermassive black hole within a system and not a binary. We don't really have a surefire kind of evidence of what an electromagnetic signature from this kind of system would look like. So this is pretty different from, for example, in the LIGO case, where they're looking for binary neutron stars. They kind of know what they're looking for when it comes for electromagnetic signatures. You have the gravitational wave signal, and then you would see a gamma ray burst. You would see a kilonova in kind of the optical infrared part of the spectrum, and then this afterglow. So they really clearly know what they're looking for when it comes to binary neutron star mergers. But when it comes to us, we're not totally sure. So that ambiguity coupled with these large areas presents kind of this hard challenge that we have to work with. So the way that we're going to kind of just start to tackle this is to get a sense of just how many galaxies might be in a localization area of this size. And we're going to do that using Nanograv's catalog of massive galaxies. So this catalog was made from the 2-mass redshift survey. So this is an infrared survey. The catalog has sky coordinates, distances, and black hole masses for about 45,000 galaxies. And this goes out to a redshift of about 0.05 or 300 megaparsecs. And we expect that the catalog will go out to slightly farther distances, 500 to 700 megaparsecs for kind of those most massive galaxies that would host these kinds of systems. So if you're interested in reading more, knowing more about the 2-mass redshift survey, for example, or this catalog that we're going to be using, I have some papers here linked. And let's go ahead and just read in the catalog, look at its contents, get familiar with it. Oh no. Oh, I'm in the wrong notebook. Okay. Here we go. Let's go ahead and read it in. So in this first cell, I kind of just have basically the just straight up contents of what the catalog looks like. So here it'll give you a description of what each column is and the units for each column. There's some notes here too. So this catalog, like I mentioned, has names. The names basically just correspond to the galaxy's coordinates. It has the distance for each galaxy and then the black hole mass for each galaxy. And there's flags here as well. So there's FDist and FBH mass. These are just telling you how the distance and the black hole mass is calculated. Some of them, for example, for the black hole mass, you might have kind of a more precise measurement, and then in some cases you might have a less precise measurement. So that might play into things as well. And we also, for some galaxies, have 2 estimates of the black hole mass. So you'll see there's an FBH mass, F bulge 1, and then bulge 031. So these are for galaxies that were estimated using this relationship between the mass of the black hole and the mass the mass of the stellar bulge in a galaxy. For some of them, we don't know the morphological type, and that means we have to make some kind of assumption about how many stars lie within, or what fraction of stars lie within the stellar bulge. So that's just kind of 2 different estimates for the black hole mass for some of those galaxies. But we're just going to work with this assumption that these are all kind of just elliptical galaxies. So this F bulge 1, meaning the fraction of stars in the bulge is 1. So basically the galaxy is just entirely a bulge. So then this is just a kind of plain text file. We can read it in very simply, and then we're going to separate out the columns into different arrays. So we're just going to work with the location, the distances, and the black hole masses. So having read that in, let's convert the sky location coordinates to RA and DEC. It'll be kind of easier for us to use later on, and this might take a second. And so first in this section, we're just going to take a look at the distribution of properties for all of these galaxies to get a sense of what we're working with. If you've gotten your coordinate conversion done, feel free to go ahead and run the next cell. And this is going to plot all of the galaxies on a sky map. So you're going to see something that looks like this. It's a lot of galaxies. But you'll notice that there's this empty U-band shape here, where we don't have any galaxies, and that is where the galactic plane is of our own galaxy. So, as you might imagine, our plane has many, many stars in it that are kind of hard to see through to observe other galaxies other than our own. So that's why this catalog doesn't really contain any galaxies in this region. This, of course, would make it pretty difficult, for example, if we detected a gravitational wave source in one of these regions and we don't really have any galaxies to work with and see if any of those galaxies are the one where the gravitational wave signal is coming from. But at least for this example, we're going to just use our example chain, which has a localization area somewhere in this region, so we won't have to worry about that. So having looked at the galaxy catalog across the sky, let's look now at what the distribution of distances and black hole masses looks like. I think I might have this as a kind of fill it in cell. Yeah, so just go ahead and plot a histogram of the distances in the catalog and the black hole masses in the catalog. The black hole masses are already given in log solar masses, and the distances are not. So you might want to plot the distances in log as well. I think that's not what I've done here, but I do have an extra comment here. So it really doesn't matter. You could do it either way. If I ran it like this, it looks pretty similar. But so our galaxy distances are all kind of peak around 100 megaparsecs or so. They go out to as far as 700, but maybe kind of tail end ends around like 400 megaparsecs or so. And then our black hole masses, a lot of them are at around 10 to the 8th solar masses, or 10 to the 9, kind of tail end here in the 10 to the 10, as well as the 10 to the 6. So I think there was definitely something I wanted to mention about the black hole masses, but maybe I'll just come back to it later. So kind of having a sense of what our galaxy catalog makeup looks like, let's go ahead and start calculating how many galaxies lie within that localization region that we were looking at before. So I have this kind of handy function here for you, and it's going to take in an array of the host coordinates, so the galaxy RA and the galaxy DEC, and then the normalized sky map from before. You can give it a credible level. This zoom parameter is going to give you the option to plot a zoom in. So sometimes you might have localization areas that might be a little bit rough to see on the full sky map. So this gives you the option to kind of zoom in on that region in particular. And then we'll come to this kind of second mask parameter later. So go ahead and run that to get that set up, and I'll walk through what this does here as well. Feel free to run the next cell as well to get the sky map plotted. Again, I have it printing out here, the true credible level, the area, and then it'll give you the number of galaxies in the region. So the way that we do that is to kind of transform the host galaxy coordinates to the axes coordinates. And then we make a mask that will kind of mask out galaxies that are not inside the localization region. And we just do that using a function within matplotlib to kind of check whether a point lies within a boundary. So I would encourage you to maybe walk through this function a little bit later if you have time, and kind of see how it works, break it down, print things out if you need to. So we're gonna take a look at this sky map here. So we're dealing with about 1,400 potential galaxies in this region. We can see it's pretty heavily clustered here, even in the zoom in, very kind of heavily populated with galaxies that, you know, might be our potential galaxy where the gravitational wave signal is coming from. And just a quick note here too, we started with about 45,000 galaxies or so, and by taking only the ones in the localization area, we've eliminated about 42,000, which sounds like a pretty big number, right? This is 97% of the catalog, but I just want to caution you, don't let percentages fool you, because at the end of the day, we're still left with about, you know, greater than 1,000 galaxies that we have to sift through to figure out which galaxy is our true host galaxy of the supermassive binary creating our gravitational wave signal. So I think kind of at the end of the day, the number is what matters the most, right? If we have you know, thousands of galaxies, we can't do EM follow-up on every single galaxy. But if we can get down to, you know, 20, maybe 10 or so, that's a lot better. So now that we have about 1,000 galaxies in this region, maybe we can use some other kind of host properties to actually start to discard the number of potential hosts. And so before we get into that, which will be this last little bit, I'll pause and just see if there are any questions.
We have one question in the room, Lena.
Okay.
Yeah.
I was just wondering if there was any sort of useful heuristic for determining what credible interval would be good to use in this sort of situation.
Yeah, I am not too sure myself. I think kind of the standard in gravitational wave localization studies has been people will sometimes in LIGO do 50% and 90%. And I think 90% is kind of like, I don't know, maybe a conservative case or so. I really just use 90% because that's pretty much the standard, but I don't know exactly how people kind of came to use that as the standard, so.
Cool. Thanks.
Yeah. I wish I had a better answer. I don't know, maybe I should look into it a little bit more, but yeah. Anything else?
That seems like it's all for now.
Okay. All right. So I know it's at time. Maybe we can run through this again really quickly. So now we're entering into kind of a really exploratory area, which is trying to figure out how we can cut down on the number of potential host galaxies. So again, we have about 1,000 plus candidates, and we need some kind of other information to be able to maybe narrow in on which galaxy is the true galaxy. So our galaxy catalog that we're working with contains distance and black hole mass estimates. So let's see if we can use that information in some way to cut down on the number of galaxies. So first thing we're going to do is implement a distance cut. So we didn't sample directly in the distance in our continuous wave analysis, but we can take our samples on the frequency, the strain, and the chirp mass and convert that into samples on the distance using this equation here. So let's do that. And then do that conversion. We're going to work with the log distance samples since we kind of sampled in log frequency, log strain, and log chirp mass. I think that makes the most sense. And then we're going to do a pretty simple, straightforward cut. So we're going to work with our credible intervals again. This is going to be a little bit arbitrary, but we're going to take a 95% credible interval and cut out any galaxies that fall outside of this interval. So we're going to take, for the 95% credible interval, we want the 2.5 percentile and then the 97.5 percentile. of our posterior distribution. So we're kind of taking our the information we got from our gravitational wave analysis and using that to cut down on galaxies. So go ahead and run those next few cells too. So this is giving you a visual of what that cut looks like. So this blue histogram is the distribution of our posterior samples on the distance from our gravitational wave analysis. And then these red dashed lines are showing you that 95 credible interval. So anything that's outside of it in the tails is what we're going to cut out. So if we go through our galaxy catalog, or specifically the ones that just lie in that localization area, we're going to check to see whether their distances lie in these tails. If they do, we're going to cut them out. And if they don't, then we'll keep them. So that's basically what this function below is going to do. Go ahead and set that up and then run the cell after that. So the main thing that you need to know for this function is it's going to take galaxy distances, those luminosity distance samples, the cutoffs that you choose, and then a mask. So this mask is what we got from our sky map plotting here. So this mask is basically just an array of the same length as the galaxy array that you put in. So for each galaxy, it'll basically have a 0 or a 1 based on whether it's masked out or not. So if it has a 0, it is within the localization area. And if it has a 1, then that means, yes, it's masked out and it's outside of the localization area. So we need that to go into this distance cut function here. So then at the end, it will return a kind of a combined mask. So it will take, the mask of the sky first, and then go through and check if it lies in the tails of the distribution. If it does, it'll assign a 1 to it and mask it out as well. So once we've done that, we made our sky plus distance mask, and then we can check to see how many galaxies remain after the distance cut, and we're left with about 1,000 now. So to visualize this, go ahead and run this cell after that as well. And you should see something that looks like this. So this is where that second mask parameter comes in this function. So this second mask, you would supply it with something that is the sky plus some other parameter kind of mask. So in this case, we did sky plus distance mask. And then so whatever kind of second mask you supply it with, it'll plot the points in gold now. So we can see in this zoom in, I don't know, maybe it might be a little hard to see, but I'll try to zoom in here a little bit. We have those turquoise points. Those are ones that fell within the localization area, but they didn't pass the distance cut, and so we cut them out. So we can see we did a little bit better in this case. This 95% credible interval distance cut, it helped us a little bit. We cut down about 300 galaxies, but we still have, somewhere on the order of 1,000 potential hosts in this area. So yeah, I guess we can kind of check in here in terms of timing. I have some more kind of exploratory things here for y'all to do if you're interested. For example, you could go back and try different cutoff values. So instead of using the 95% credible interval, try using a 68% credible interval or a 50%, and see how much better you can do in cutting out potential galaxies. The distance cut function that I supplied you with also has the option to do just a single value cut. So say you only wanted to take, galaxies that lie in the kind of upper 10% tail and cut those out. You could do that, or the lower 10%. You could cut those out as well if you wanted to do that. So feel free to kind of play around with that a little bit. And then I'm not sure if we'll really have time to go through in the rest of the notebook, but there is an option for you to do a cut on the black hole mass as well. It's going to function pretty much exactly like the distance cut. And I think at that point, that might be about it. At the very end, I think I'll kind of just close out with this. It's really important to make sure that you do a true galaxy check. So you could, try different types of cuts and see how well you can do in cutting down on the number of galaxies, but you want to be careful and make sure that you don't cut out the true galaxy that you injected into in the first place. So this is kind of for a simulated case. Of course, if we have a true continuous wave detection, we won't know which galaxy it's coming from, but that still means that we need to be really careful in making sure that when we do these galaxy cuts, we're not cutting out the true host. So I have a few spaces here for you to do that and check to see whether the true galaxy survived your cuts or not, and then you can go back and modify that as needed. And then there's some bonus material as well for a little bit more advanced cuts if you're interested in that. But yeah, I think I'll just stop there.
That was really great, Polina. Thank you very much for that. Do we have questions? Anything about the procedures done in there that you want to know about more? Okay. I think we still have some time where people could take about 15 minutes more to explore some of the other cells in here. How much longer would you think it would take to get through some of the bonus material, Paulina?
I mean, the bonus material is really kind of more advanced stuff that if people are interested in doing that, you can kind of do on your own time and think about it a little more. But we could maybe get through as well the black hole mass cut. That's pretty similar to the distance cut. So if we have another like 10 minutes or so, that would probably be good.
Okay, so another 10 minutes is absolutely fine. So
okay.
If you think you can get through the mask cut, and then after that, we'll go outside, try to take a group picture, because I've realized I've forgotten to take pictures the entire week. So we need to get a picture of all of us here at the summer school, and we'll take a little bit of a break after that, and we'll wrap up after that. So, Polina, yeah, if you've got more on mask cuts, go ahead.
Sure. Well, how about I give y'all a few minutes to go back and try a few different options for the distance cut first. So yeah, like I mentioned, what you want to do is just go back in this kind of percent cuts array that we made earlier up here. And try putting in different values there. So like I suggested, you could try the 68% credible interval, which would be percentiles of 16 and 84. You could try a 50% credible interval, so 25 and 75. So you're taking the middle 50%. And then as well, if you want to try a single kind of boundary cut, try that as well. So I'll take maybe like 2 minutes or so and let y'all play around with that. So you'll need to kind of change those numbers and then go through all of the cells up until this plotting function. All right, hopefully you've had a chance to try some things out. I will go up here and just show you, for example, let's try 50% credible interval. So you can see how that really narrows in on a slimmer part of the distribution. And then that leaves us with 515 galaxies. So we kind of cut in half from the 95% credible interval to a 50% credible interval. And you can see too in this kind of zoom in here that really changed how many gold colored galaxies we have since we cut out so many more galaxies. But I'm going to go ahead and change this back to what it was. Rerun these things. And then we're going to go ahead and move on to this black hole mass cut. So the black hole mass cut is a little bit more involved. In our galaxy catalog, we have a black hole mass estimate for each galaxy. And this was done with a variety of methods. So they're not kind of uniform in the way that this black hole mass was calculated. And so they have different uncertainties related to them. But for our purposes, we want to assume that this black hole mass estimate is kind of a total binary mass. So we're assuming that, you know, each of these galaxies does have a putative binary within it, and we're going to take the black hole mass estimate to be the total mass of both black holes in the galaxy. When we analyze pulsar timing ray data, another kind of more complicated thing involved here is that we sample over the chirp mass of the binary, and that is not quite the total mass of the binary. They're related with this relation. So the chirp mass is a fraction of the total mass, and it will also depend on the mass ratio of your binary. We don't really have any information about the mass ratio when it comes to gravitational wave searches. For individual binaries, we don't really constrain it at all. So we have a few options in terms of some assumptions that we can make. So one is we can just kind of assume what the mass ratio is reasonably. We expect that pulsar timing ray sources are going to be coming from major mergers. So major merger just meaning that the mass ratio is pretty large, so greater than 0.25. So this mass ratio is kind of the ratio of the smaller black hole to the larger black hole. Another kind of option that we have is to draw from a range of mass ratio values. So you could, you know, set up a normal distribution or a uniform distribution, maybe ranging between this major merger kind of range of values between 0.25 and 1. And just sample different mass ratios and calculate the total masses that way. If you want to be a little bit more sophisticated, you can also use rejection sampling to kind of decompose your chirp mass posterior into a posterior on the mass ratio and the total mass. So just really simply, we're gonna just make an assumption here that every binary in our case has a mass ratio of 1, so equal mass binary. So with that assumption, we're going to convert our chirp mass samples to samples on the total mass. And then I'm going to have you plot 2 histograms here just to give you an idea of the difference between the chirp mass and the total mass. So again, like I mentioned, the chirp mass is a fraction of what the total binary mass is. So it's always going to be less. But from now on, we're working with this total mass posterior here in orange. So we're going to implement exactly the same type of cut here as we did for our distance cut. So it's just going to take the black hole masses of all of your galaxies, the total mass samples, some cutoff values, and again, that mask from your sky plotting. So go ahead and run that. and then choose your cuts. So I think at this point it gets a little bit more exploratory. Feel free to put in whatever kind of credible interval you want to look at here. Again, you could just choose one value and it'll take, you know, either the lower or the upper tail. You could also choose like a credible interval in the middle of that distribution. Once you do that, I'm just gonna skip ahead here to what my version looks like. So here again, I'm just looking at the 95th credible interval. Again, to plot it and to see what that looks like. Our total mass distribution is pretty narrow, but it's going to cut out any galaxies that lie in these tails. We're going to make a combined mask with the sky and now this black hole mass cut. And if we do a credible interval cut of 95%, we're left with just 78 galaxies after the cut, which is pretty amazing. Going from, you know, 1,000 plus to 78 galaxies after your black hole mass cut. Let's see what this looks like on the map as well. And you can see that in the zoom in here, we have a lot less of these gold colored galaxies as well that survive the black hole mass cut. So yeah, I just have kind of like a summary question here. You can feel free to play around with different mass cuts as well, try different credible intervals. If you go kind of more stringent on your mass cut, how many galaxies are you left with? Can you do better? And yeah, kind of explore that kind of thing. I guess one thing that's kind of might stick out to you here is that the mass cut tends to do a lot better than the distance cut. So the reason for that is because we kind of, you know, sample directly in the chirp mass, as opposed to we don't really sample in the distance very frequently, especially if you're using quick CW, we're not sampling over the distance. So maybe some things in the conversion there don't really, you know, produce distance posteriors that are really very informative, whereas on the mass, we have much more stringent posteriors. And so that helps to kind of cut out additional galaxies. But like I mentioned before, go through and change some of those black hole mass cut parameters and see what you get, but also make sure that you go through this last part and you check to make sure that your true galaxy lies in that list of galaxies that remain after your cut. So I've given you here the sky coordinates for the true galaxy, and I have this kind of left blank in the tutorial version, but if you look at the solution version, if you need a bit of a hint, basically we're just going to check first to see if the galaxy remains after the distance cut, and it does. If we check to see if it remains after the black hole mass cut, though, we can see that the true galaxy was actually cut out from our cut. So maybe that's not entirely surprising considering that we started with about 1,000 galaxies or so, and then after the mass cut, we were left with 78. That's a pretty drastic cut. So it's maybe not quite surprising that our true galaxy is not among those that remain. But yeah, I think with that in mind, also feel free to go back, change your mass cut, see what changes. Here in this bonus material too, as well, I have a few hints here about different things you could try. So like I mentioned, the black hole mass cut can be a little bit more sophisticated. I have some options here for you to try things out. And then to kind of give you a sense also of why maybe the mass cut didn't work quite so well, the mass ratio that I had for this continuous wave signal was really, really low. So our mass ratio assumption at the beginning of a mass ratio of 1 also probably had an effect in which galaxies were cut out and why our true galaxy wasn't there at the end. So using that information, feel free to go back, change things. I'll mention too that this mass ratio is really, really low. It's not really what we expect to see with PTAs. This was just done as like kind of a test run. And then I have some space here for you as well, if you're interested in the future of trying kind of a combination distance and black hole mass cut. I've plotted here the posteriors, the kind of 2D posterior on both the total mass and the distance. So that's shown with this histogram here, and then all of these white points are all of the galaxies in the catalog, and you could kind of look at where those lie in relation to each other, and also take a look at out of these white points, which ones are within the localization region. Can you use this kind of 2D combined posterior to cut more galaxies? And then also, if you are feeling bold, you could go back and look at the original galaxy data that came from the 2-mass redshift survey. So I have a file, a directory in here that contains the actual survey file. And that contains things like different infrared band magnitudes, the morphological classifications for all of the galaxies. So you could even try playing around with some of those things and see if you, for example, only took elliptical galaxies, how much of a change would that make in your cuts? If you tried to do kind of a K-band magnitude cut, what would you get if you do that? So really a whole lot of different things that you could try here in the future if you're ever interested. But yeah, I think that kind of wraps things up. Any kind of final questions or anything?
Any last questions? Okay, and again, I'm sure if you have questions, when you look at this later on, just let Paulina know. All right, everyone, that pretty much wraps up everything for the summer school. What we're going to do now is, while I still have your attention, we'll go outside and try to find somewhere to take a picture of everyone. And then we can take about a 15-minute break before we come back, and I'll wrap up things for everyone. Okay? Thanks again, Paulina.
There is a group, that's,
That was my quick attempt at photoshopping. Celia Walajian at some. No, Neva's in there. Neva's, yeah. Yeah. All right, so for the folks online, we're just wrapping up here. We came back from a break and some people are already playing chess on a Friday afternoon. But I did want to thank everyone that contributed to the lectures and everything surrounding the summer school this week, particularly Karanjani, Abimanyu, Nima, Kyle, William, Jesse, Luke, even though he couldn't be here. We definitely used some of his materials. Polina, Maria, and Andrea Mitradates. So let's all give them a round of applause. Thank you, that's very nice, but it wouldn't have been possible without, and I mean that, it wouldn't have been possible without the help of people like Kyle, William, and who am I forgetting? Other people in the group, that Manuel, Aaron, other people in the group that have really helped out this week with logistics and coming in early, making sure the coffee's here, helping with the lunches, and particularly Raina Beach, our admin. She's not here, but she's done an amazing job ordering all the food and making sure it's in this week. Nima is our tech wizard and made sure that we were online every day. So thanks to all of them, and let's give them a round of applause. I wanted to wrap up by quickly kind of giving you my impression of what the important questions for this field are in the next 10 years or so, and things that would be important for your careers when you're thinking about questions that are important. So ultimately, I feel in my gut that the gravitational wave background signal that we're seeing is mostly supermassive black hole binaries. The vast majority is supermassive black hole binaries. But we don't have a solid way of demonstrating that, or at least a clean way of showing that. We can argue it statistically, but we don't have priors that help us say this is definitely black hole binaries, and it's definitely not cosmology. We can get constraints from other kind of cosmology experiments, which would limit how much those signals could be. We can't just ramp up gravitational wave signals from the early universe and think we can get away with it, because that would violate constraints from the CMB and from Big Bang nuclear synthesis and other experiments. So I think within the next couple of years, we'll see the emergence of more rigorous techniques for statistically saying how much of the background could be of cosmology origin versus astrophysics. Ultimately, we also have to ask how much information we can get from the gravitational wave background spectrum. It is still a fuzzy quantity that has been constrained, and ultimately it's a series of maybe 10 numbers, which is the power of the frequencies we can access. And they're not perfectly estimated, so they have some uncertainties. There is limited information in this signal that we're seeing. So again, it's kind of like we're looking at a background signal that's similar to the CMB, but the CMB has the ability to imprint fundamental physics with an accuracy that the gravitational wave background currently does not have. So there might still be limited information we can access here. In order to build more confidence, I think we can try to cross-validate the signals we have among the different PTA experiments, but also with completely separate experiments that happen to access the same frequency band. And that's astrometry that Celia mentioned earlier this week. It just so happens that the frequencies do serendipitously line up, and we could try to think about the problem as kind of a deflectional four vector, where pulsar timing is doing the temporal part of the deflection vector, and then astrometry is doing the spatial part of the deflection vector. If we can combine all of that together, we could get more information about the signal. But I think now that we have this evidence for the background, we're starting to fill in some of the details, and really the next big milestone is finding an individual source. And if we can find an individual source, that can help us build a stronger case that the origin of the background is binaries, right? Because, and this hasn't been formalized as an argument yet, but you can imagine that if you find a single gravitational wave source, then that gives you a stronger confidence that, oh, that background signal I saw before is probably composed of binaries as well. And we're just starting to see the signal break down into individual signals. So what will the emergence of individual signals look like? What does that story look like? Will it be one of these paths that Polina mentioned, Maria mentioned earlier today? Either a targeted search on candidates that we have already, in which we build confidence in those and claim that we see gravitational wave signals from those candidates, or will it be an all-sky, completely untargeted search, which gives us broad localization, and then we start kind of just ticking off the ones where we think that there are no binaries in those galaxies. And then again, what Maria mentioned this morning, can we do multi-messenger astronomy in a meaningful way with pulsar timing arrays? and spectroscopic binary candidates and photometric variable candidates, and really tell a more complete story about a particular system by taking in lots of different data streams, gravitational waves and pulsar timing, flux variability in the optical from something like the Vera-Rubin Observatory, and then Sloan giving us kind of spectroscopic variability. And that would be really exciting. And then I think we have to think about what unique or complementary fundamental physics and cosmology can be done with this field. There are lots of other experiments and there are lots of other ways of trying to constrain beyond GR theories of gravity, including massive gravity theories, ones that include additional polarizations beyond the plus and cross polarizations we've talked about this week. I don't think we've even mentioned that in a completely general theory of gravity, where the geometry is defined by a metric, that g mu nu, you can actually have up to 6 polarization states of gravitational waves. But it's by making those Lorentz gauge and then TT gauge choices that you reduce your degrees of freedom, and that's what defines general relativity. So when we talk about beyond GR, we can have 6 polarization states. Some of them are actually longitudinal. That is, the deformation of space-time is in the same direction as the propagation direction. So can we probe any of that? Can we probe details about the polarization information in the signals? Can we say something about early universe signatures, primordial black holes, inflation, phase transitions? Could we even use some of the gravitational wave signals we measure as standard sirens and measure the Hubble constant, something like that? So there are lots of questions to be asked, and I think it's just a case of looking at the information content within the next 10 years and trying to see what we can realistically measure. Once we get beyond 10 years, we get into the era where LISA is launched, and then we'll have to think about how this field sits alongside LISA as a complementary way of accessing massive black holes. LISA will not access the same systems and same population as what we can access, and so we have to look at it like it's a series of tandem experiments. Now, when they're working in tandem, they won't be looking at one source evolving from PTAs into LISA. Unfortunately, that won't be the case. That kind of situation can happen where a source goes from LISA into LIGO, or whatever is the successor to LIGO. But the timescales involved in PTAs and LISA just don't work out where we can see the evolution of the same signal from one band to the other. So it becomes a game of statistics, which is why we've spent so much time this week talking about statistical methods. So this is just a rough idea of what I think are important questions for the future. I'm sure as you get into this more, you'll start asking your own questions and carving out your own piece of this. And hopefully this week has gone some way to helping you get started or build on the expertise you already have. So thanks so much. All right, so that's everything done. Now we have to decide for those who want to go out and celebrate the end of a successful week, what we should do. So this is really just into the brainstorming phase. I have very few ideas other than going to